A very good evening to one and all present here. I am Dr. Trupti VN, the co-coordinator for the ATAL FDP. On behalf of Faculty of Engineering and Technology, JAIN deemed to be university, uh, I welcome each and everyone for today's inaugural function. This inaugural function is about the AICTE sponsored ATAL online FTP on power electronics applications in microgrid using AI, which is, I request all the participants to kindly mute yourself. Before we begin with the formal inaugural function, I seek the blessings of Almighty. I request Dhatri for the invocation.
Good evening to everyone. I'm Katkan Reddy. Now I'm going to sing a song. Ganesh. गणनायकाय गणदैवताय गणाध्यक्षाय धीमहि गुणशरीराय गुणमण्डिताय गुणेशानाय धीमहि गुणातीताय गुणाधीशाय गुणप्रविष्टाय धीमहि एकदन्ताय वक्रतुण्डाय गौरीतनयाय धीमहि गजेशानाय बालचन्द्राय श्रीगणेशाय धीमहि. Thank you for giving opportunity.
Thank you, Dhatri. Now I request Dr. G. Eliarison, HOD of Department of Electrical and Electronics Engineering, for the welcome address.
Can you hear me, Tripti?
Yes, sir.
Yeah. Yes. Yeah. Good evening and warm welcome to all. It is my distinct pleasure to welcome you to the inaugural session of the 5-day ATAL online FTP program on the topic power electronic application in microgrids using artificial intelligence. This program is being organized by the Department of Electrical and Electronics Engineering, Faculty of Engineering Technology, FET, JAIN deemed to be University, Bengaluru. We are delighted to have our distinguished people from our management. First and foremost, I thank the Honorable President and the Chancellor of the JAIN University, the Vice President of the JAIN Group of Institutions, for giving us the opportunity through JAIN University. I would like to extend a special welcome to our Honorable Vice Chancellor of JAIN deemed to be University, Dr. Raj Singh, whose visionary leadership continues to guide and inspire the growth of our university, fostering a culture of innovation and excellence in education and research. We are also privileged to have with us our Honorable Registrar of JAIN deemed to be University, Dr. Jitendra Kumar Mishra, whose steadfast commitment to academic integrity and administrative excellence has ensured smooth functioning of all our programs. It is my honor to welcome Dr. Hari Prasad, the Director of FET, in his absence, whose directions and encouragement have been instrumental in organizing such a relevant and cutting-edge program that brings together the field of power electronic microgrids and artificial intelligence. In her absence, I am also delighted to thank Dr. Sharda Kanwar, the esteemed Chief Academic Officer of JAIN University, who, with their vast experience and exceptional leadership in the field of education, provides invaluable insights and vision to our academic community. We are also grateful to the fraternity of the JAIN Group of Institutions for their constant support in fostering an environment of continuous plays a crucial role in enhancing the academic experience of our students and faculty. A warm welcome also goes to all the heads of the department, faculty members, and researchers whose valuable contributions help shape the future of our institution. To the participants joining us from various parts of the country, we extend our heartfelt greetings. Your enthusiasm for this advanced program demonstrates your commitment to learning and applying emerging technologies that will play a transformative role in the field of power electronics and artificial intelligence. Over the next 5 days, this FTP will provide in-depth insights into the integration of power electronics in microgrids, with a particular focus on how artificial intelligence can optimize their operation and efficiency. We are fortunate to have a series of expert sessions lined up, which will delve into latest research, practical application, and future trends in this interdisciplinary field. I will like to express my gratitude to all our speakers and facilitators for their valuable time and effort in making this program an enriching experience for everyone. Once again, I welcome you all and I wish you a fruitful and insightful journey through this FTP. Thank you.
Thank you, sir, for the welcome address. Now I request Dr. Raj Singh, the Vice Chancellor of JAIN deemed to be University, to address the gathering.
Thank you so much, ma'am. Distinguished Registrar Dr. Mishra, Director Dr. Hari Prasad, heads of the department, colleagues, can I appeal all of the participants to please mute the audio? A lot of background noise is coming. Thank you. All my faculty colleagues, research scholars, delegates, speakers, and dear students. Thank you so much for having me this evening for the inaugural function. I congratulate the organizing team to put together this FDP, which will go on for next 5 days. I also thank the AICTE for sponsoring this program, and each one of you, the participants, without whom it wouldn't have been possible, for taking out time and being with us this evening. Friends, if you just go back into the past not too long ago, maybe just 4 to 5 years, I personally believe that whatever existed in terms of systems and processes in the landscape of higher education before 2020, it has completely changed. And if that be so, and I've seen it all happening over the last almost a decade, some changes started from 2015, but all of them were summarized and the direction was given in the form of national education policy. So if that be so, whatever we knew before that, one, we have to unlearn it and learn new things. You cannot have structured program. In any case, you don't have structured programs for higher education teachers. The only method is conducting these kind of faculty development programs so that they're up to date, they're able to take on the challenges of the future, and also implement what changes have taken place. Above all, apart from learning the technicalities of all the regulations and guidelines which have been published by not only UGC, but all the statutory bodies and governments, we need a mindset change, because to bring in any change, first we need to accept that change is required, understand what changes have come in, and then learn how to implement so that we successfully do that. And this all will lead to quality improvement of higher education. The aim of national education policy is not only to groom students who are professionally competent, but also make them citizens who are sensible and sensitive to the needs of the environment, the society, and the community, and also have sense making, in the sense what decisions they take, what they do should be for the larger masses. So those kind of objectives being there, I think one thing is for sure, that we not only need to teach technical things, but also have a blend of humanity, the social science, and other disciplines, so that they have wider understanding of this. This particular FDP, I can see having participants from all over the country. I presume that it consists of a diverse group. May not be coming from branches other than engineering, but at least within engineering, they come from different specializations. And therefore, it provides an excellent platform for all of you to interact and see the interconnectedness, see the interlinkages. And my request would be that as you go through the FDP of 4 days, ask questions, share your best practices so that each one of us jointly stands to benefit and enrich. Outcome-based education as a part of national education policy, I believe, is the soul of NEP. Because this is one framework which connects almost everything, not only the directions given by NEP, but also what we do at the institution level, department level, program level, and the course level. I think the entire acumen of faculty members is put to test. There's a different issue that we articulate, but we don't do it. But I think unless we implement everything on ground, it becomes difficult to achieve what is aimed to be achieved. Electrical and electronics engineering is one such field which, according to me, is witnessing maximum innovations. If you look at signal engineering, for example, let's say the railway system or the metro system, which more than 40 of them are either operational or about to be operational. About 85% of the role is of signaling, with directly links to electronics. And there are electrical trains. They're not based on the fossil fuels. And if you look at the degree of automation, I think it tells the entire story, that what kind of innovations and changes we are going through. If you look at battery charging stations for electrical vehicles, they need to be charged. And to look at the sustainability and the renewable source of energy, one thing which is being thought of, that can charging of batteries also be through the renewable sources. So for example, one of the concepts which we were discussing other day in one of the conferences, we had an expert from UAE who said they're exploring the possibilities of charging the batteries at different places. They have been, of course, put in place, but the biggest challenge is how to charge them. You need electricity for that. Is that electricity coming from renewable sources, or it's also causing pollution? The recent example is in Delhi. If you look at the pollution problem, we kept blaming for last so many years stubble burning in Punjab and Haryana, but the real reason we found was thermal energy, because it consumes coal, and that has caused such a degree of pollution that the living of the people is becoming very, very difficult. It's a hell. So unless we look at from sourcing of the inputs to disposing of the final product and using sustainable processes, sustainable means of energy, will not be able to bring in sustainability in true sense. So one of the possibility being discussed was that to charge these batteries on highways, can you look at generating solar energy during the daytime when the sunlight is there? Evenings, normally you find very strong winds. So can you look at wind energy by installing windmills? And post midnight, can you look at biogas? So all three of them being connected through 24 hours of supply of electricity. Now this opens up an opportunity for us to innovate, to develop systems and processes, to bring in innovation. I'm just giving one of the examples. There are many of them. Can you design buildings which are self-sufficient, which are green buildings? It's happening all over the world. And considering the targets of Agenda 2030 of United Nations, I think as countries, we need to be on the front foot and bring in innovation to find sustainable means and processes. Now, if you look at electrical engineering as a discipline in engineering colleges, I know it's not doing very well. Across the country, we find less and less admissions because the craze of computer science and IT. We need to understand that unless the core branches are strengthened, what kind of IT-enabled services we can think of. It's a cycle, and it's likely to see the downward trend after seeing uptrend of last 4 to 5 years. I'm personally very, very upbeat about the core branches, whether electronics or electronics being the mother branch. Electrical, civil, aerospace, mechanical, all the branches for that matter. Because electrical vehicles, which is the future, or sustainable processes in all the industries, which is the future, cannot be achieved unless all these branches are strengthened and they work interactively. They work together. They find common grounds for innovations. And therefore, for students, faculty, and researchers, there's a huge scope for bringing innovation. And then fortunately, we have the enabling technologies like AI, which is mentioned also in the title, and many other technologies, for example, data analytics, cybersecurity, cloud computing, which can help you handle a large amount of data. We are able to do certain things which are otherwise not possible. My request would be that please look at all these possibilities and how we as academic institutions, whichever institution you come from, innovate and contribute to the innovation system of not only the country, but also the entire globe. That is what is expected of us. I welcome all of you once again. Thank you, Kishore and other faculty colleagues, the HODs, and under the guidance of Dr. Hari Prasad, to put together this FTP, which I'm sure will make each one of us enriched over the next 5 days. Thank you for having me, and I wish you all the best. Thank you so much.
Thank you, sir, for
Sir,
your wisdom
Kirti,
of
ma'am.
words. Thank you, sir, for your wisdom of words, sir, and motivating us to organize this type of FTPs further. Now I request Dr. Jitendra Kumar Mishra, sir, Registrar, JAIN Dingtobi University, to address the participants.
Thank you, madam. Honorable Vice Chancellor, Dr. Raj Mishra, our Director for FET, Dr. Hari Prasad ji, HODs of the departments, uh, participants, facilitators, ladies and gentlemen. It is indeed an honor to be part of uh, part of teaching fraternity. We are forced learners. The students have the liberty and choice to attend the class or not to attend the class, to write an examination at a given point or not to write the examination. But we as teachers are always on schedule and we have no option. Once we commit to be part of the teaching fraternity and we uh, choose to be a teacher, we have to go to classes, we have to undertake the facilitation, and for making it enriched, we are forced to learn on continuous basis. We don't have any choice. But if you see over last few decades, the conventional way of learning and that the faculty members have been blamed for carrying the old PPT and old notes have faded away because the knowledge has been evolving at a very fast pace. The innovations has been happening at unprecedented pace. And also the entire contour of learning teaching has been redefined. When we entered the dot-com era, when www was invented, we had a different perspective. The boundaries of geography and the location, the time, everything started losing its significance because through internet you can connect to any place, anytime, and you can have access to larger body of knowledge and learning has expanded to a great deal. That was very exciting and interesting. We all enjoyed that frame. Further, after invention of AI, as we see that it is acquiring larger space in all domain of learning and all walks of life, the teaching learning is getting redefined once again. And on one hand, it is very exciting to learn the newer domains which are opening up because of AI facilitating the newer ways of learning, access to newer domain of knowledge. On the other hand, it is challenging also because a lot of things that we are very proud of and that were distinction are becoming hygiene. Even our students knows through the application of AI. And that is when we need to understand that how we can use this opportunity, this newer dimension of the technological innovation to enrich teaching learning and make it optimum. So rather than questioning or getting into its debate that whether it is working in a way or not, we need to use it. We are having this FDP, which is going to help us expanding our understanding from whatever we have been knowing in the domain of power electronics and its applications in power grid. we are going to explore that how AI can give it a new dimension, give it a new direction. And that learning over a week time will certainly make us more effective in classroom, in our lab. And otherwise also, it will open new dimensions of thought, thinking, new collaboration it will force, and we will be able to build something new at the front of our research or in the domain of our teaching. So it's wonderful to be together, having, being together as a cohort of learners is always a privilege because we all learn from each other as much as we learn from any source, whether it is a book or the digital resources. Learning from each other is far more effective because it is not a passive learning. On the contrary, it allows us to think in different direction as we bring a different way of looking at different approach to looking at the issue of learning and the problems in general. So I'm sure that being together for a week time, having great facilitators who are lined up for facilitating the sessions and thinking together on the newer dimensions which are opening up in the field of power electronics and its application to microgrid in the age of AI, how AI can be used to facilitate it better, will make us much richer in terms of our understanding, also more proficient in terms of our delivery in the classroom and effective in terms of our research. I take this opportunity to compliment the organizers for their thoughtful designing of this FDP, the facilitators who facilitated it to see the light of the day, and also my uh, appreciation to AICT for coming forward and sponsoring it. It's very heartening to note that uh, in last decade, the regulators has been of great support to facilitate learning rather than being constrained and being uh, conservative in facilitating the newer areas. They are upcoming. On the contrary, they have started working as a prompter. They start sharing the newer areas of learning, newer dimensions of learning, and they keep prompting the academic institutions and the faculty members to take initiative and capitalize on the facilitation that AICT or UGC or other regulatory bodies are bringing up and encash on that. So let us make use of this opportunity where learning has become really very exciting and interesting, where everything is converging to explore newer dimensions. I wish you that over a week time, you will have good friends, you will have newer topics of collaboration, and you will have better understanding on the topic. I wish you all very happy learning. Thank you very much. Thank you.
Thank you, sir, for motivating the organizing team and all the participants. Uh, Now I request Dr. Kishore Kumar P, the coordinator for the ATAL Online FDP, to give a brief just about the FDP.
Thank you, madam. Good evening, one and all. So first of all, I like to thank AACTE for trusting me personally. So this is my second AACTE event conducted by me. One I have conducted in the previous institution and one in this institution. And I thank ATAL Academy also for continuously giving the opportunities to JAIN University. It shows our efficiency and our effects in teaching and learning from JAIN University. And my sincere thanks to our chairman, sir, who is the main force for all of us to start any event and to apply for any event. And my special thanks to VC sir and Registrar sir. Whenever we come and ask for the inaugural function, they are immediately accepted and they have supported us like anything. And my special thanks to our HOD sir, Elderson sir, and my co-coordinator Trupti madam, and all our faculty members of electrical and electronics engineering. And coming to this FDP is 6-day FDP, and each day we are having 13 sessions completely, and each day 2 sessions. Yeah, this is the schedule what we have shared, Madam is shared. So the sessions, what AACT is sifarsing for us, that means 2 resource persons from foreign countries and half of the resource persons from industry. We have followed all the norms, and coming to the participants, we have 196 participants from 11 states. So we feel that that shows the effectiveness of the program, because it's from AACT and we have already disclosed our what we can call, we have already disclosed our brochure and we have already disclosed our schedule also. That means they can come to know who are the remote renowned persons we have selected. And from academy also, we have half of the faculty members, they have contributing their work, and many of people are from IITs and NITs, and remaining people are well researchers from different universities. And coming to FDP, the FDP name is Power Electronic Applications in Microgrid Using Artificial Intelligence. So we basically concentrate on microgrid. Microgrid contains of different renewable, combination of different renewable energy sources, maybe solar and wind. And we have come up with some battery management systems and battery storage systems. So that is a broad area, and we want to narrow down to power electronic applications only. That means how power electronic is utilized for getting the solar energy into electrical energy, and how power electronics is utilized for getting the wind energy, converting the wind energy into electrical energy, and controlling aspects also. So with these insights, we have narrowed down the complete microgrid topic into power electronic level, and then we want to extend the same thing up to the artificial intelligence level also, so that we have touched the transdisciplinary and multidisciplinary also. And artificial intelligence, for getting a very good artificial intelligence software system, we should have strong hardware also. For that, we have incorporated one very good lecture from very good foreign speaker on VLSI design. So this is also one of the best topics we have selected out of this particular topic. So like this, the FDP has distributed. So I have discussed about the FDP. I have discussed about the resource persons and participants also. So now this is a call for all the participants, how best you can make use of these things. And as Mishra sir and Raj Singh sir has already disclosed their views on this topic and this FDP. So based on this, we can go ahead with how best we can get good friends and how best we can move forward in our research or learning on microgrid and artificial intelligence. And being the research coordinator from electrical and electronics engineering, you can also make use of our services in research domain, and you can also collaborate with us. Okay, this is an open opportunity for all of us, because some of the people are from IITs, so we can collaborate with them. Some of the people are NITs, we can collaborate with them. And remaining people are from different universities, but they are very good researchers, so we can always collaborate with them. So my sincere request would be, try to utilize these 6 days for getting the knowledge and also getting the very good contacts. Okay, and as you already know that 80% attendance is the mandatory and 70% of marks in the test is mandatory. So I wish every one of you have fruitful 6-day FDP, and everyone should get this certificate, and we will definitely help you out in this aspect. But we require your kind support in attending the classes regularly and sincerely, so that you can easily write the test easily. Okay, so with this note, I like to conclude. So I once again welcome each one of you for the ATAL online FDP on power electronic applications in microgrid using artificial intelligence. Thank you. Thank you so much. Trupti madam.
Thank you so much, sir, for giving the complete insight about the 1-week FDP program.
Thank you.
So we would like to conclude the inaugural event. Firstly, I would like to thank AICTE for sponsoring the online FDP, and also I would like to thank the ATAL Academy for trusting in us and giving an opportunity for the online FDP on power electronics applications in microgrid using AI. I would like to thank the Chancellor, Dr. Jainraj Roychand, for constantly supporting us and motivating us to organize such events. I would also like to thank Dr. Raj Singh, Registrar, Vice Chancellor, Jain deemed to be University, Dr. Jitendra Kumar Mishra, sir, Registrar, Jain deemed to be University, Vice President, sir, Professor Bandari, sir, for motivating us constantly to come up with these FTPs. And I would also like to thank Dr. S.A. Hariprasad, sir, Dean Academics and Director of Faculty of Engineering and Technology for constantly supporting us and encouraging us. I would also like to thank Dr. G. Eliason, HOD of Department of Electrical and Electronics Engineering, and also would like to thank the faculty members of Department of Electrical and Electronics Engineering, both teaching and non-teaching, for helping us in conducting this FTP. And lastly, I would like to thank the facilities department and CC team and the management for helping us in conducting this FTP. Um, Thank you all. I also like to thank all the participants for joining this FTP. I hope you'll get a beautiful insight of this FTP, and I hope it will be a knowledgeable session for all of you. And hopefully we will connect after this FTP session also. So thank you once again. We will begin with the day one session in another 5 minutes. So day one, we have two sessions, session one and session two. In another 5 minutes, we will be beginning with the session one. Kindly stay online. We will start with the session one in another 5 minutes. Thank you once again.
Hello.
I request all the participants to be online. In another 3 minutes, we will begin with session one. I request all the participants to switch on their video for a photo session. I request all the participants kindly switch on the video for the photo session. Dear participants, kindly switch on your video. Thank you so much. Kindly be online. We'll begin with the session 1 in another 2 minutes.
Ma'am, has my photograph come? Because I had gone for a sec. Ma'am, you are mute, ma'am.
Madam, I have captured all the participants. So I'll be sharing once the session completes.
No, am I there in the pic?
Archana madam, I have taken your photograph, madam. No need to worry.
Okay, sir. Thank you.
Yes, I have taken, madam.
Okay, sir.
Yeah, we will share among ourselves and we will share with you also.
Good evening once again. Good evening once again to all the participants and the resource person. Now we are going to begin with the session 1, which is titled as Microgrid Technologies. The session 1 is on microgrid technologies. The speaker for session 1 is Dr. Kodeshwar Kumaran, who is an associate professor from MSRIT College of Engineering, Bangalore. Dr. Kodeshwar Kumaran has completed his undergraduate studies in electrical and electronics engineering in the year 2001, and he has obtained his master's degree in power electronics and drives in 2002. He obtained a doctoral degree from NITK Surathkal in 2018. He has been working as a faculty for the last 21 years. He is a certified LabVIEW associate developer and a consultant from GDembed Solutions, assisting in the design and development of intelligent instrument panels, condition monitoring systems, and embedded controller-based design. His areas of interest include embedded controllers, high-power converter applications, and special machine drives. We welcome you, sir. I request you to begin with this session. The session is all yours from now.
Thank you for that introduction, madam. Am I audible?
Yes, sir, you're audible. Sir, you'll be sharing the PPT?
Yes, madam. I'm sharing my entire screen.
Okay, sir.
Can you tell me whether it is visible?
Yes, sir, it is visible.
Yes. Good evening, all of you. I would also like to thank the coordinators, JAIN University and AECT, of course, for inviting me to share my knowledge and the points of view in this particular faculty development program. And the title which is mentioned in the brochure is the Microgrid Technologies. I have taken the freedom to modify it a little bit. My forte is in embedded controllers, and when I told Kishore sir, he said you have to talk about microgrid technologies also. So I'm going to, of course, we are going to have a discussion on microgrid technologies, some of those standards and related things. And then we are going to see things related to embedded controllers actually. So this session will be of two parts. The first part will be for us to recollect our understanding of microgrids, grids, and things associated with this power system, electrical power systems. And the second part is going to be related to implementational aspects. It's not software implementation, it is a hardware implementation. So as much as possible, we will have a discussion in this particular 1.5 hour session. To just give you a context, sorry, I think, yes. Is my presentation visible? I think I did something.
No, sir.
Just a minute, sir.
Yes, sir.
How about now, sir?
Yes, sir. Yes, sir. It is visible now.
Okay, thank you for confirming. Just to give a context of our today's session, I thought of including some information. Energy always has been a kind of interesting thing for human beings, and we can say that we are attracted to energy in a way, and whoever produces energy and utilizes energy efficiently, they lead the humankind. In that way, if you see this particular chart, the information what is shown in this particular chart, we can see the US and the rest of the European countries, they consume almost half of the global electricity, electrical energy. So obviously you can assess that being a developed country, they are consuming this much amount of energy. And we in Asia, we are nearly 1/4 of this consumption. And this particular consumption is supposed to rise, the projected demand is supposed to rise, which means that we are also trying to catch up, and we are shortly going to become a developed country. If not very shortly, at least in a short span of time, we may come to that particular level. Now, if we look at our energy production scenario, we have these kinds of data. I pulled it from the government portal, National Power Portal, what we call shortly as NPP. The kind of installation what we have in our country, it amounts for around 450 gigawatts. And the chart at the bottom, the pie chart, it shows that majority of this energy comes from thermal power plants. So these kinds of thermal power plants include the ones fired by coal, gas, diesel, all those nuclear things, which converts water into steam and generates electrical power from them. And little less than 50% is the share of the remaining power sources. And if we look into the chart, pie chart carefully, the other sources are in fact catching up. They are in fact catching up. And this is where our microgrid concept comes into picture, and the usage of microgrid comes into picture. And in the next slide, I have included the information about who is generating how much. The top pie chart incidentally shows what is the percentage generation of from that 454 gigahertz. What is the percentage generation by the government entities and the private entities? Interestingly, if we notice, more than 50% of the share, the lion's share, comes from the private entities. And all of these plants, incidentally, at least most of them, they are thermal based plants. They are something like coal mostly, some are
முந்தி இந்த சேர்க்குள்ள போய் இங்க வச்சு
உங்க பேட் ரெடி பண்ணிட்டேன் அப்படி வச்சு எழுதுற மாதிரி
அதை கீழே வச்சு எழுதுற மாதிரி.
Could the participants mute yourself? Can you just mute the participants' mic?
Please make yourself.
So private sectors which are generating this electricity, most of them, they are catering their generation from thermal based plants, and of course renewable based plants, they are also picking up. They are also picking up pace. Can the participants mute your mic? Okay, we will continue with the session. The bar chart at the bottom, I think still it is not muted, sir. Okay, I think now it is better. The bar chart at the bottom, if we observe very carefully, the demand is being met by the generation plants. And incidentally, there are some facts which we before discussing anything related to the slides, I will just like to point out certain facts. On May 30th of this year, on May 30th of 2024, there was a projected demand of around 235 gigawatts. 235 gigawatts. That was usually power Grid India Corporation. Now that is a new name from they have given it to the earlier entity. So this particular entity, they have the projected demands which are being assessed by the computers and given it to them. And based upon this, they used to have their plans as backup for meeting up the excess demand and all those things. So the projected demand was almost like a 235 gigawatt. But on that particular day, the demand shot by almost 15 gigawatts. It was almost 250 gigawatt. 15 gigawatts of power was in excess what was projected. Still, we didn't see any blackout. We didn't see any major shutdowns, or we didn't see any major problems. That is how sophisticated our country's power grid corporation has come. The Grid Indian thing which manages all these power routing and trading, all those things. It is how sophisticated it has become. All these things are because we are increasing, as a country, we are increasing our generation capability continuously. So this particular graph on this slide, it gives us an idea about how this generation capacity is being increased by our government. Of course, we have to thank our government, the bureaucrats, the engineers, and of course academicians like us who helped to bring the country to this particular stage. Now on the top left, we have the capacity installations of hydroelectric power, and we have the thermal next to it. On the bottom, we have nuclear and renewable energy sources. We don't have much of a provision to increase the generating capacity as far as hydro is concerned. We know how water is a precious resource and how constrained it is as far as our subcontinent is concerned. And increasing the thermal power plant capacity, of course, it is possible, but since we are a signatory of that United Nations Framework Convention for Climate Change, UNFCCC, even this year we had a conference in, I think, Baku or something. So that particular convention, we are signatory of that particular convention, and we have agreed to abide by the international laws to keep this pollution, climate change thing under control. So that is going to be a restriction for us to increase our thermal capacity. And of course, we can go for increasing the nuclear power plant capacity, which is going to take place, but it may not be at a very fast exponential rate. So the only option which is left out for us in our country is to increase the installed capacity by using these renewable energy sources like our solar power plants or off-grid offshore wind power plants, or even the fuel cell plants which might catch up very sooner, and things related like that. And we do have a large scale solar power plant installation in our country. I think it is in 2.75 gigawatt or something Badal power plant or something. So we do have, but we don't have that much. That is set to change. We are going to see more and more such installations in our country. And this is exactly our microgrid is going to come into picture. We are going to see about those things. Okay, this is just to give you a context about how the government entities are increasing the associated capacities for transmission distribution. Now coming to the microgrid part. So most of these energy sources in these grids, I mean microgrids, they are going to be distributed energy resources, what we sweetly refer to as DERs, distribution energy sources. And most of these are comprised of solar power plants majorly, and some wind power plants, and maybe minor other entities too. Now these kinds of installations very frequently we have seen in our colleges, or perhaps hospitals, or any other smaller kind of installations. So these installations, they cater to the need of a particular community or a particular locality, in the sense that these generation sources, they cater to a particular geographic footprint, and unlike our major grid, which takes care of the entire country, state, or a large area, microgrids cater to a small geographical footprint. And this particular microgrid concept is going to pick up. That is what at least the projection is. We do have microgrids. It is going to pick up pace as time goes on. Now, these kinds of microgrids, they consist of the power sources. They do consist of course, the loads, the consumer loads, and we do have the sophisticated controllers, and we do have the energy storage systems. So these make up the components of the microgrid. So in each and every one of these places, improvement is possible, especially when it comes to microgrid controller. We can, as academic community, we can do tremendously to optimize this controller to deliver power more efficiently, to utilize the power more efficiently, reduce the losses, and have a lot of things done. And that is exactly what we are going to discuss in this faculty development program. Some of the key characteristics of a microgrid, it is local, independent, and intelligent. And of course, wherever we have these DER resources, they are going to be local, catering to the local entities. So this means that we don't have to look for the power coming from a power plant which is located far, far away. I might not, sitting in Bangalore, I might not expect the power from Raichur or probably the private power plant entities near Mangaluru or something like that. So this tremendously reduces the transmission losses, and that itself is one significant factor which is going to increase our efficiency, the overall efficiency. So we do have certain advantages of having the DERs in local entities, and it is completely independent, of course. So we can have our own reliable power supply source just next to our doors. And since these kinds of microgrids are having a vision of the entire subcomponents of a microgrid, we can call these microgrids as intelligent entities. So the microgrid controllers, whose structure we will be seeing shortly in the presentation, these have a communication channel with all the subcomponents of a microgrid. So this enables the controller to be more intelligent. Of course, the necessity of the microgrid, it is reliability, resilience, most of all, energy independence, efficiency, and the most attractive feature of all, the environmental sustainability, which is going to be of major importance in the coming days. So some of the critical functions for the operation of our microgrid, they are listed here. Three primary things are being listed here, the major critical functions. One is the black start capability. As the name says, it is the ability of the power system to come back to life after a probable blackout or a outage, might be of any reasons. The second one is a surge capability, the ability of the microgrid to withstand the transient changes. Most often we would have observed when a high power motor is being switched on, immediately we would have seen a kind of flicker in our utility connected appliances. So anything which takes care of this kind of transient conditions is what we refer here as a surge capability. And last, of course, is a major thing and the important thing what we do, maintaining the line voltage and frequency. So these are considered as the critical functions in a microgrid. And the challenges and opportunities for microgrids comes in three different forms. First is the cost and funding challenges. The second one is the regulatory challenges. And the third one is a technical challenge. The first and the third one, there is nothing as academic community we can do to approach it and find out a solution for. But we can do things related to the technical challenges. So we can, of course, start with the energy management systems to make the microgrid the best energy management system. So this can be done in plenty of ways. It can start by optimizing our power conversion components which are a part of our microgrids, then we can focus on the kind of algorithms. We do have existing algorithms which are good enough, but there is always a scope for improvement. And especially with the advent of AI, we will see where and all we can increase the efficiency, optimize the performance. We will shortly see that the standards, what we are going to see, we will try to find avenues where we can incorporate our innovations there. And things related to anything related to energy management, everything we can keep our hands on. So this is a particular thing what we are supposed to focus as a part of the academic community, and we can have n number of researches done on these aspects. Now, putting all these things together, developing a sophisticated algorithm, having an algorithm to manage the supply demand, manage the load profile, all these things we can put it in three major categories: to manage the power flow, to maintain stability, and of course to take care of the low inertia. So by inertia, we mean something which is related to the amount of power generated by our microgrids. So in the one of the previous slides we saw, microgrids at the maximum cater to a maximum of few megawatt. So of course, this means that our transmission, distribution, and power production, the entire power system, electrical power system, EPS, they have a low inertia. Any big motor, say a 100 watt, 100 kilowatt, say a elevator induction motor, if it is switched on, of course they will have some sort of compensating mechanism. Still, it creates a disturbance in our transmission lines. Since we are connected to the grid, not microgrid, since we are connected to the grid, this kind of disturbance is almost like nothing to the grid. But when we are talking about energizing these kinds of bigger loads from a microgrid through the bus which comes from the DER resource present in the microgrid, then of course it is a point of concern for us. We have to even think of this lower inertia which is present in microgrids. So this is another view. So these are the major three things which we are supposed to focus on and cater to those issues. Now coming to the microgrid types, we have different types of them with different categories. Each of those categories are categorized based upon different factors. Some of them I have listed it here. Based upon the type of bus, we might see a microgrid which is of AC microgrid type, or a DC, or a combination of both, which is referred as hybrid. Sometimes we very simply call these grids as on-grid and off-grid, the ones which are connected to the grid. When there is outage in the grid, we switch back to the islanded mode where we use the distributed energy resource. That's what we call it as a grid connected microgrid. And the one which entirely operates in the islanded mode, the other one. So as the name says, a DC microgrid has a DC bus, and this DC bus derives its power from the distributed energy resources. So we do have certain advantage when we go for a DC microgrid. The most important or most attractive advantage of all these things is that we don't have to worry much about the control. We don't have to bother about synchronization, or we don't have to bother about frequencies, at least when we are talking about DC loads and non-grid connected modes. We don't have to bother much about all these things. So that is a beauty of DC microgrid, but there is of course limitation. So only DC loads can be connected directly to the DC microgrid. If you want to power up AC load from a DC microgrid, obviously we need to go for a power conversion, DC to AC, and then we have to plug those AC components in. So this is just to recollect the ideas and things we have already learned. So let us not dwell deep into these. So the AC microgrid, as the name says, the bus is AC. So you have certain advantage. Naturally, you have certain limitations. And keeping in view of the emergence of electric vehicles, two-wheelers and four-wheelers in our domestic houses, domestic applications, we have to think about a way where we can reduce the converter losses, AC converted to DC, and this DC processed properly to charge our vehicles. Obviously, we see a lot of power loss there. So this is one limitation there. But on the other hand, most of the loads being AC, this might be a good thing. But always a combination of both might look attractive, and that is where our AC microgrid comes into picture. So if we can club both the advantages of AC and DC, then we get a hybrid microgrid, which looks something like this. So you have interconnection mechanism in between, which interacts between the AC bus and the DC bus. And obviously, we have the advantages of both of these. So naturally, we do have a limitation. The complexity increases when it comes to hybrid microgrids. Control complexity and the structural complexity also. Now, I thought of mentioning a few things related to smart grids, primarily because of, let me skip through a couple of slides. Yes, looking into this particular data. So this is a data which was proposed by the relevant minister on the Honorable Lok Sabha, in the Honorable Lok Sabha. So this was in reply to a question posted in Lok Sabha. If we see this particular chart briefly, if we look into it, we can understand what is a power outage time which has happened in each year. So this data, and of course the next slide, we have one more data. We have similar kind of question asked in the Lok Sabha, and it was answered with the relevant details. If you see very carefully to the values listed there, we are able to see the individual states, individual metro cities, how much power was, we can have similar kind of data, power outage, power supply, power demand, all these things. So all these things, it was available to NPP because it was being collected by intelligent entities, and that is where our smart grids comes into picture. So manually, a person who is managing the localized centers doesn't need to send these details. Automatically, all these details are logged and it goes to the NPP, National Power Portal. So that is how these smart grids started coming into picture. And we have smart grid version 1.0, 2.0. Now it has advanced beyond having smart meters and smart logging, these kinds of primitive functions. We do have certain functions what we see in the literature mentioned as energy internet. Just like the data flows through the cables here and there from one system to another, from my system to your system, from your system to some other system, energy also can be routed there. Now, if we see, we can see the architecture of a power net, where we are able to see the interconnects, the power stations, the isolation switches, and then the monitoring points, all those things. If we see the figure on the right side, so one of the interconnects, they are being implemented using power switches. So this diagram shows power switch, individual power switch. In the actual scenario, we will have n number of devices connected in series parallel to take care of the voltage and current requirements. So these are the routing networks what we can see there. So our power electronic interfaces, they can be used in this way also. So far we would have seen our power switches, which makes them as a part of the converters alone. Hardly we would have seen these kinds of architectures. So these are also forming as a part of the smart grid architecture nowadays, the advanced smart grid architectures. So we can see similar kind of architectural diagrams in the literature nowadays. A complex architecture is being managed very efficiently through wonderful algorithms. And this is one venue where you can go for sophisticated algorithms, not rule-based, but fuzzy-based or AI-based. We can go for it. There are a couple of interesting things we can see from this atmosphere. For instance, if we look into a solar power plant, based upon maybe the irradiation levels during the different points of days or the cloud cover, the generation capability might get affected. Or sometimes whatever the generation capability is, the absorption by different loads, it might create a short moment transients. And these transients, they always can be taken care by the energy storage systems like batteries or ultra capacitors. And these things require sophisticated controllers. Once again, where I'm linking this particular point is the microgrid controllers are supposed to do all these functions, just not routing the power, just not controlling the power, managing the power most efficiently. So all of these are avenues for us to take up our research works, not just existing solutions. We can come up with much more wonderful algorithms than what we have right at this point of time. Now, each of these things what we can do, they are being standardized by standardizing agencies. We will look into that shortly. The microgrid control as such, it is implemented in 3 different levels. They call it as primary level, secondary level, and tertiary level, or sometimes they are called as level 1, level 2, level 3 control. So if we look into it, the level 1 control is more closely associated with the microgrid, whatever things which are present near the microgrid, the topmost hierarchy, topmost hierarchy where you have the tertiary control, level 3 control, it is associated with the functions which are closely arranged near the grid. And the secondary control is sitting somewhere in between these two. So the functions which are supposed to be controlled at a device level, at the local level, those are being primarily discussed in one of the IEEE standards. Not this one, next one. We will discuss that shortly. Okay. So there are not lots of standards, quite a few standards which we can refer to when it comes to implementation of microgrids. The most important of all is IEEE 1547. So this standard is for interconnecting DER sources with electrical power systems. So it has many parts. Some of those parts are yet to be released. Some of those parts are still waiting for approval. The parts which have been approved and which is being in use, in force, they are listed here. So if at all we are going to do anything which should make a practical difference, we need to consult to these standards. We need to conform to these standards, whatever these standards are saying. And our own grid code also closely follows this IEEE 1547. Some of the provisions I have listed here, like there are certain things which might be of interest to you. For instance, if we look into the third point, the distributed resources in the labs must be able to run parallelly with the main grid. And the second line of it says, without causing voltage fluctuations at the point of coupling as greater than plus or minus 5%. We do have existing systems which can control and conform to this particular tolerance level. That doesn't mean there are no further scope of improving. So now we have here an option which is varying in the range of plus or minus 5%. We don't have any rule-based kind of thing, unlike the previous points mentioned there. Now this is a scope for us to use fuzzy-based algorithms or things related to AIs. We don't have solid things there. Like that, in the standard, we can identify provisions where we can put into our AI algorithms to use to enhance our optimization strategies, to enhance the system performance. And like that, we have a few more things. I have not listed everything, only a few points are listed here. Yes, so in this particular slide, if we see the third point, it is related to the harmonic current injection. And we always have seen that the harmonics need to be kept at the level of 5% maximum at the point of coupling, point of interface, POIs. It should be kept at 5%. This is another wonderful avenue for us to employ all our AI algorithms and other things. We do have rule-based algorithms, but we have a tremendous opportunity to apply all your AI-based algorithms which can cater to meeting this particular requirement regarding the harmonic distortions. And what we see in the top first one, it is a rule-based one, which we can straight away implement using formula-based relations. It is just like a condition which can be expressed using a regular equation. Okay, we do have one more point. I'll skip on this. Now we'll come to microgrid controllers. Now you may have idea about where I'm trying to take this presentation, where I'm trying to lead you. It is all coming down to how effective our controller can be designed to take care of all these things. Now, controllers, by controllers, I don't just mean an algorithm. By controllers, I mean a physical entity, something like a processor, something like a embedded processor, something like DSP or any. And the functions of the controllers, they are also the functions of microcontrollers. They are also being very specifically mentioned in one of the other IEEE standards. For instance, IEEE 2030.7 says specifically about the microgrid controllers. And the if you read this particular standard, we can, of course, boil down the operations into very simple arguments by splitting up the operating modes, steady state operating modes, into two states, as illustrated very beautifully in this image. And we can have four kinds of transitions. So the first steady state is all about grid connected state. The second steady state is all about the islanded mode. So when we are switching from one state to another state, one steady state to another steady state, either from grid connected to islanded or islanded to grid connected, there are four possible transitions which are listed here. The first transition is the transition from a grid connected state to the islanded state, and this can be a planned one or unplanned one. If it is a planned one, it is going to be smooth. So now we may get a question when it might be planned. So there are power outages which we get intimations about that prior to the power outage. It might be because of the regular maintenance activity which is going on in the transmission lines, or perhaps a unit of the generating station being pulled out for maintenance. So these kinds of things are planned activities. So in advance, the utility company gives an idea about the grid-based utility companies. They give an idea about these kinds of power outages, and they also specify the time that this maintenance will be taking place. This is what we refer to as planned transition. So we know the time at which this transition is going to be needed. So we keep some of those DERs warmed up. We don't go for a cold start. We keep it warmed up. And when the time of that particular outage comes, which is a planned one, we smoothly transit from the steady state grid connected state to islanded mode. This is a planned one. It is going to be, of course, smooth. There might be some kind of transitions from grid connected to islanded states, which might not be unplanned all of a sudden because of some reasons. The power from the grid might be unavailable. So under these cases, we have to transit to the islanded mode. And this particular islanded mode transition can either be a success or it may not be a success. So we may not have the required number of generating stations online in our microgrid when this kind of transition is about to happen. Since we don't know it is going to be planned, we cannot keep the power stations running unless and otherwise it is some kind of battery energy storage based things, or something like solar plant during the peak daytime, or something like that. If you are depending upon small thermal stations or diesel stations, that is a perfect example. We won't be running these things for conserving the energy, which means that we have to perform a cold start, and that is what we refer to here. So if at all these kinds of DERs are not running at that particular instant when the transition from grid connected state to steady state is required, then we will go for a momentary blackout. Of course, there will be blackout, and then we will start from this momentary blackout and we will go on to the black start, what we call it as a black start. Unlike a cold start, black start, we will go for it. If at all we have some kind of stations which are running and which can smoothly take over the important critical loads, then we will transit from the grid connected state to steady state. So this also is another state. So like this, we put together all these states, we get 4 transition states. And how these things are supposed to be performed, they are very clearly defined in our IEEE standard. What functions should be performed by which component, where it should be performed, all those things are mentioned there. I have not put extra points related to 2030.7. It is accessible only on a paid basis. We won't be able to access it unless we have a subscription for these things. So if at all you have access to this, there are plenty of power consultants tutorials available where we can get access to these kinds of things presented in the standard 2030.7. You can always refer to that. Now coming to the power converters used in microgrids. So if we observe this particular layout, we can understand how important our power electronic converters are. They act as interfaces between one part and the other part, between one component of the microgrid with the another component. So we might have these kinds of power converters, power switches, which are just merely acting as a switch, which acts as a sectionalizers, isolating one section from the another, or it might be used for modulating the power as such. The next diagram in this next slide gives us much more clear idea about the role of power electronics in a microgrid. So if we observe this very carefully, this is a very primitive layout, but still it gives us an idea. We have a couple of energy sources. The power is being processed by the power converters. Of course, the power converter need to be controlled in order to process the power, and that is where the localized microgrid controllers comes into picture. Usually, the microgrid controller as such, it will be something like a sophisticated computer, something like a part of a SCADA system. These kinds of SCADA systems might be interacting with the local controllers, and this is where our embedded controllers comes into picture. So these kinds of controllers, the control of these kinds of things boils down to controlling the power switches, which means that we will be issuing appropriate gate signals in an appropriate way to these power switches. It might be for isolation, connecting, disconnection. It might be for modulation, any kind of things. In order for this particular local controller to work, we need the information from the controller, the feedback information, the control information, all those things need to be there. So we do have a requirement on this controller part that it should be able to process the information, communicate the information, and control the information. So now in this particular diagram, we have illustration of how a power semiconductor switch is used as an interconnect, just as a thing which connects and disconnects it. So it performs a mere open close operation. Of course, it cannot be used for controlling the power, and that becomes a part of the power converters. So we have different kinds of power converters depending upon what actually we want to do. What is it, just merely processing the magnitude, or is it changing the power from one type to another, AC to DC, or DC to DC, or DC to AC? It might be anything. Depending upon that, we might have different topologies of these power converters. Each of these different topologies are formed by different ways in which these switches are connected, and that is exactly where we have the processing intelligence requirement, the control from embedded controller, which is required here. I'll just show you some of the converter topologies which are found on the literature. Isolated topologies, non-isolated topologies, different versions of them. So on looking at these slides figures, one thing is clear, that we do require localized controllers, and these localized controllers should be in the form of some kind of processor which are embedded into these localized systems, and these controllers perform some function. It senses certain environmental parameters, in these cases the current, voltage, frequency, things like that, and it takes a decision what kind of control should be issued to the power switches, how it need to be controlled. Is it just isolation or is it modulation also? Then you need certain other functions like communication, which need to be performed by these microcontrollers. So the localized controllers might want to send these information to the centralized controller, and these controllers might be interested in receiving the information from the centralized controllers. So communication also becomes another important job that need to be performed by our embedded controllers. Now, keeping all these things in mind, we can conclude that certain functions need to be performed by our embedded controllers when we are looking into implementing the microgrid related control algorithms or microgrid related converters. There are certain functions which need to be performed by the microgrid controllers, starting from sensing to control and communication. So those functions, yes, we do have different kinds of converters, and we sense the parameters using different sensors, transducer mechanisms. We have the current sensed by the current transformers, voltage by potential transformers. Sometimes these Rogowski coils also comes into picture when we are trying to measure current. Yes, now coming to the main discussion about embedded controllers. So we can assess now that these are the things which are supposed to be part of our embedded control systems. We need to have some sort of processor electronic brain. We need to, of course, have a power converter which performs the conversion. We need to have some sort of transducer sensor network, and of course we need to have essential thing, communication network. So if you recollect, in one of the previous slides we have listed that microgrid is intelligent. So this intelligence comes from processing the information from each of the subcomponents of a microgrid, and that is why this communication also becomes a very essential part of our embedded controllers in our microgrid. Now, all of these things are hardware related things. Before we put to use all of these things, the integration of all of these things, we might be interested in checking these things. We might be interested in testing our system before we put it into use. And that is where the model-based testing platforms comes into picture. So we will delve into these things a little bit in the forthcoming slides. Now, there are plenty of targets which we can possibly use. I have taken one target because I have been using this for almost 10 years now. So C2000 is my favorite. Of course, you can use any other targets also. ST has a wonderful portfolio of targets. Some other companies also may have wonderful targets. So I have taken C2000 architecture from controllers from Texas Instruments. They have very sophisticated functions embedded into those controllers of this particular family, C2000 family. And we do have every single option available, every single option required in these controllers, whether it is a simple reading of a simple data from, say, a current data or steady state current data or voltage data, or to read transient data, which requires you to take more number of samples in a short span of time, or whether it is to process a sophisticated algorithm, any sophisticated. In its simplest way, you convert the three-phase quantities. Once you sense all the three parameters, you convert the three-phase quantities into two-phase quantities, then the stationary frame. These kinds of things are kind of computational intense. So obviously you need a processor, an electronic brain, which can process this information in a sophisticated manner and very fastly. So our electronic brain, it should be having a data bit of sufficient data size, preferably 32 bits or something like that, or at least similar to that. And it need to have specialized processing algorithms, something like a dedicated hardware, like a dedicated multiplier or things like that, in order to accelerate the computation. Then you need to have different peripherals like the ones which will help you to control the power switches, maybe to generate PWM signals or to sample the data, ADC data. So all these things, if it is in the form of a peripheral, then it takes the processing load from the processor. The processor doesn't have to monitor these things intensively. It can just inform the peripheral, do this particular job, and the processor can do other things, processing the information, which is, of course, the most important one. So we have to look into the kind of peripherals available on the target also. And of course, you need to look into the kind of peripherals which focuses on communicating the information to the other entities in the system. So all of those things, we do have a beautiful set of peripherals in C2000 architecture. We can perform sensing of any parameter what you want, like voltage current using ADCs, or capturing the information about frequency using capture modules, processing the sophisticated algorithms using control law accelerators, dedicated hardware multipliers, fixed point units, or generating, issuing appropriate control signal for modulation to your power switches, which comes from the EPWM peripherals and high resolution PWM modules peripherals. By the way, these kinds of high resolution PWM modules are very much important if at all you are working with SiC or GaN based converters. You might have those kinds of requirements. And of course, the communication interfaces like CAN, Modbus, I2C, those kinds of things. Now, all of these put together should be able to give us a real-time control, because these are real-time systems. Obviously, we need to have a real-time control, and this real-time control can only be obtained if at all the target which you are going to use in your intended design is having a combination of all these things, all of these sophisticated peripherals, the sophistication in the controller, the other aspects, everything should be integrated into a single chip. So we often call these things as digital signal controllers. Instead of DSPs, we call it as a DSCs. Unless and otherwise we have a sophisticated DSCs, real-time control may not be possible. So this is one thing we will be looking for from any target. Any target which satisfies these requirements are potential candidates for your design. Now I'll just briefly mention about where this model-based design fits in. As the name says, the design is going to be model-based. So we won't keep our hands. Let's skip these slides. I'll go to the next one, and then if required, we will come back to the previous slide. So these model-based designs, they help us to avoid expensive hardware iterations. We prefer simulations. Simulation is the first step in testing any system. Beyond simulation, we have to proceed to the next levels of testing also. So we will see in the next slide what are the other levels of testing. So the primary intention of having a model-based design framework is to avoid expensive hardware iterations. We would want to test our system, whether it will be able to cope up and whether it will be able to perform in the same way as we have intended it to perform. And we do have other advantages of MBDs, which are listed, of course, here. And I'll skip all these things quickly. So any model-based design development will have these following steps: modeling a plant, analyzing and synthesizing a controller for the plant, simulating and integrating all these things by deploying them the controller. Yes, this is a main slide I want to spend some time on. When it comes to testing a system, usually we will be preferring simulation packages where we will be putting all the components of a system. In this class of a microgrid, we might be putting the distributed energy resource. It might be a solar or it might be wind-based, or it might be any other similar kind of things. We will have the source, we will have the load, and we will have the processing things in between, like a different power converters. We will have the appropriate controllers which control the power flow from the source to the load, and the energy controller which manages the energy flow from the source to different loads. And you might have priority algorithms too to manage the flow of energy. So in microgrids, there is one important thing, what you call it as environmentally sensitive. So you need to have idea about your microgrid controller, need to have idea about what kind of loads it is energizing. So all of these different kinds of load profiles and the priorities of these loads should be available with the centralized microgrid controllers. Only then it will be able to make a wise decision. In case there is a power shortage, it will try to energize the critical loads. Then it will look for the other non-critical loads. The management system should be taking care of all these things, energy flowing from the source to the load. All these things we would have put up in our simulation model. We would have tested it. It would have run very quickly. But when we try to implement it on a hardware, we might not have seen these things running up so satisfying in a satisfactory manner. That is because always there is a little bit of difference between what we get out of the simulation and what we see from the hardware. And that is why we need to go for other forms of testing also, other form of verification and validation also. So we have another three levels, another three types of testing. The ones what we call it as a software in loop, processor in loop, and hardware in loop. So model in loop purely talks about simulation. Now, whatever job which our controller is supposed to do, the digital controller is supposed to do. So those things are converted into appropriate C codes. Code gen, we use it to convert it into appropriate C codes. Now we make this C code as a part of our model. Then we run the model, we observe the performance. So when we try to test our system in this fashion, it is referred as software in loop simulation. It is called as software in loop simulation when we have the C codes which are supposed to take care of all these control aspects being a part of the model. So this is a little bit better than model in loop simulations. Now in the next phase, we actually dump this particular control algorithm. So your code generated C files obviously will be converted to object binary files, and which in turn will be put up in your program memory of the embedded controllers. Now we dump this particular algorithm on an actual processor, physical processor, but the rest of the other things, the complete plant model and the rest of all those things will be part of the computer environment. It will be part of the simulation environment. Only the algorithm will be running from the processor. Now this way we will be able to see how well our processor, the embedded controller, is able to respond to different cases. Now this is a little bit advanced version of testing, which gives us a close result as possible to the actual hardware results. Now this is a next level of simulation called as processor in loop, and we will be seeing a short demo, very short demo of this particular processor in loop using Altair tools. And the last one is what we refer as a hardware in loop simulations. In order to perform hardware in loop simulations, we need to have dedicated hardware which emulates the actual plant, whatever plant we have in, if we are talking about microgrid. That microgrid plant's model is emulated in terms of hardware, whatever voltage which you can see as a part of the bus, the current which is flowing to the loads, all those signals you will be able to get it from this hardware, which is mimicking the, which is emulating the microgrid. Actual system is being emulated there. Now this particular emulator, this particular hardware signals are being interfaced with the embedded controllers, the electronic brains, what we have used in the previous section, the processor. Now this hardware, which is emulating the plant, is allowed to interact with the processor, and in this way we try to observe how best our system is responding. Now this is the best kind of testing what we can do to check how good our actual system in the actual plant is going to be behaving like. So that is a next level of thing. But of course, this is going to require us to have specialized hardwares. So it might not be feasible for all of us to adapt for this. But definitely we can go for software in loop, maybe the first one model in loop, next software in loop, or if not, skipping the directly coming to processor in loop simulations. So once we have verified our results here using processor in loop simulations, we can almost be certain that if at all the model is responding as it is supposed to in the PAL simulations, we can be sure that the hardware response also, hardware results also will be almost the same as that of what we have got in PAL simulations. We have different tools what we can use for realizing these things. Now on the hardware side, the targets can be from any of the manufacturers. As I told you, you can use C2000 controllers, or you can go for STM controllers or any other controllers, of course. On the hardware side, I've listed only a few of them which I am aware of. I have personally used Altair for a very long time, since it was called as Vissim in 2014-15, and then it was taken over by Altair. Almost 10 years I have used, and I find that I have also used LabVIEW and also MathWorks, embedded coder based things. And this choice, I shouldn't sound like I'm giving preference to one particular tool, but it looks like it is having certain advantage. You can evaluate it and you can decide it for yourself. So what I'm trying to say is you need to have a hardware target, something like this, and you need to have a software platform which will help us to take forward this model based design test and validation to the next level. So a typical environment will have something like this. It doesn't mean it has to be Altair. Since I have used Altair, I have just projected that. I'm not promoting anything or not showing anything. Whatever I have done, I'm trying to show it here. So you have two of the softwares. There are end softwares released by Altair. Two of them are listed here. The one which you call it as embed is on the topmost diagram, and what you call it as PSIM, which many of you may have used it. Earlier it was with a different entity. Now Altair has acquired it. So you have these two things. PSIM is primarily for power electronic signal simulations. They say the convergence is very quick when compared to any other kind of simulators. When I say convergence, what I mean is as a part, when you try to model a power electronic converter, you do have reactive elements as a part of this converter system. And when we try to express this in the form of equations, you will see the derivative terms and of course the integral terms. So when we are trying to find out solution for these expressions, we always use initial conditions, or we used some sort of method in order to arrive at a final solution. And the quickness with which we arrive at this final solution, that's what I refer it as convergence. So they say, and they have shown it in one demo also, they say that the convergence is very quick here when it comes to PSIM. Of course, you have to test it for yourself. You have to convince yourself for this. I'm not promoting any software. And this is for power electronic simulation. And on this side, we have the so-called embed, which is primarily used to program embedded controllers like our C2000 targets, or even this particular embed supports our academicians' favorite target, our favorite development board, Raspberry Pis and Arduinos. They are also supported by this particular software. And the beauty of this particular software is we don't have to hand code anything. It is not a textual-based tool. It is a kind of graphical interface. So you can observe in this diagram, all you see is a couple of blocks, couple of elements. Everything is visually interpretable. The functions of all of these things are visually interpretable, which means that the time one takes to develop a code, put it to test, or to debug, that is drastically reduced. We don't have to memorize any syntax. We don't have to take care of learning any language. We just can bother about only the functional aspects, what functionality should be becoming a part of our control algorithm, how these are interrelated, how these are communicating with each other, interacting with each other. We just focus upon the functional aspects alone. So that is the beauty of graphical based programs. And all those tools what I have listed in the previous slide, the Altair tool, MapWorks, Embedded Coder, or LabVIEW, all of these are graphical based things what I was mentioning about. So you do have advantage when you go for graphical based development platforms like this. Now, when we integrate both of these, we get to do processor in loop simulations. The entire plant can be modeled on your PSIM, the entire plant, part of the plant, anyhow you decide. And whatever you want to do with the processor, with the target, those things can be controlled from here in our embed platform. Embed is the name of the software in our embed platform. So when we combine both of them, we get a powerful test results, a powerful way of testing our systems. The processor in loop testing can be, of course, done by this. Probably I'll just show you a brief demo. I'll exit the PPT. I'll I hope still my screen is visible.
It's visible.
Yes, sir.
Yes, sir.
Okay, sir. Thanks for confirming. I'll just project you this particular model first. This is a part of the example section of PSIM. We have a PV based, we can't call it as a grid, but of course, for the sake of discussion, we will call it as a grid. So you have a PV based plant, and the parameters of this PV based plant are mentioned here. You can, if you have the data sheet of any manufacturer, you can enter those details here. And that power is being processed by a two-level inverter, and that is being interfaced with the grid. You, of course, have certain filter elements and other things, controllers, all these things. So the first way of testing our microgrid model is by having model-based plant like this. You have everything modeled on the simulation platform, everything starting from the source all the way to the load, controllers, everything. They are being modeled in the simulation platform. We just run it and then probably we test the results. I think it will take I have a sampling time in the order of microseconds, so it will take a little bit of time. So we can get the results from the simulation platform. But as I mentioned earlier, the results what we get from these kinds of simulation models may not entirely match with our hardware results. So that is one minor disadvantage with our model-based simulations. So we have to move on to processor or software in-loop simulations. I'll just show you how these things use. Just one waveform. So you get to see the outputs, you get to see the control signals, all these things, you can analyze it. Now, this is one way of checking our algorithms. The next way of doing it, as I told you, is the processor in-loop simulations. I'm skipping the software in-loop simulation. I'm going directly to processor in-loop simulations. Now, I have taken a very small model here. So this is a kind of model which emulates the MPPT algorithm. So what is being done is this power from the solar panel is being optimized and then it is being provided as output. Now this is a simulation model. The entire things are in the form of a simulation. The complete thing is a simulation mode. All of those things are modeled here in PSM. Nothing is actually a hardware related thing. We don't have a physical solar panel. We don't have a physical comparator. We don't have a physical MOSFET. All of these things are software based. Now we will see how we are integrating this into hardware. Now, just for the sake of simplicity, I have done something. And by the way, the irradiation is made as a square wave. We are going to see how it is going to, the power production is going to vary when the irradiation is fluctuating. That is a motive of this particular model. And once again, this you can get it from the example section of PSIM. Now, if you observe very carefully, I think you can see my mouse pointer. I have taken the signal from the output power which is being generated by this simulation model. So I have the plant model here. The output, one of the outputs, I have taken it, and this particular output I am passing on to the embed platform. So this embed platform is one which will help us to program our embedded controllers. So in this particular case, I have selected the target as one of the C2000 family controllers. The part name is TMS320F28027, which has all these specifics. So now, whatever algorithm I have here, I'm going to compare the power level. If it is greater than 30, then we are going to take some decision. It is going to do something on the hardware. In this case, simply IO pin signal will be held high. If it is, the condition is not met, the signal will be held low. A primitive simulation, just for understanding. We can take it up to the next level. We can make it as sophisticated as possible. Okay, since it will be easy for us to understand, I have taken a very primitive way of doing this course simulation. Now, everything related to the model, the plant that is being simulated here. So this plant is going to give us the information about the power generated, the maximum power generated by the solar panel for given irradiation. Now that information is being taken and it is being sent to the actual hardware. Now this processing of comparing the output of the panel what we saw earlier, that panel's output will be compared with a value, and if at all, assuming that we are going for overproduction or underproduction, we want to do certain things. So let us assume this is one such case. So if at all the production is beyond 30, then we may want to give it as an indication to the user or send a kind of information through our communication buses to the supervisory computer. Let us say something. So this particular signal pin will be raised. Now that functionality is going to be implemented through our hardware controllers. I'll just try to connect my target here. So I'm going to click on this run button. So just for the sake of seeing the results on the screen, I have added a visual indicator here also. So as the irradiation level goes up and down like this, up and down like this, the output of the solar panel also is varying. Now this particular output is what is being fed as a data to our embedded controller, the hardware target. Now that target compares the power generated by our model, purely simulation model, and it takes the decision to control a hardware output. Now that hardware output is what you see here. I will show. I'm not sure whether this is visible. Can one of you confirm? This board, there should be a LED which is glowing on and off. Can anyone?
Yes, sir.
Thanks, sir.
Yes,
Thank
sir.
you.
That is
Now
blinking.
yeah, thank you, sir. Thank you. Now this is a result which you see on the hardware actually. Now what we are doing here, we have the entire plant being modeled on the PSIM environment. We are trying to process a portion of the algorithm, not the entire algorithm, a portion of the algorithm on our hardware target, the embedded controller, the C2000 controller. And we are actually taking a decision what to do, what kind of signal we have to send it to a GPIO pin, a digital pin. And that result is what we saw as a hardware. A very primitive way of showing you how core simulation can help us to verify the actual hardware results. These kinds of results, you can trust me, it will be almost close to the actual systems results. Of course, there are plenty of things what you have to do, like playing with the sampling rate and controlling the parameters. For instance, I have taken some sample rate here, but the rate at which my model is running is entirely different. It runs at a very fast rate. So sometimes we have to pay very close attention to this. And in the same way, when I'm trying to sample a signal, hardware signal through our controller, for instance, in this PSIM model, this analog signal, this is supposedly analog signal. If we want to process this, if we want to sample this, and we want to take up a decision like this, then we may have to use ADCs. When we come to ADCs usage, you know that you have to strictly use the required sample rate, if not more, definitely not less. It should be more, it should be as required. And then you have to do certain other configurations, like how many number of samples you want to take and how you want to process these readings. So all those things, unless we are able to configure, we might not be able to see the actual hardware results. So that is another level of discussions. Let's not go there. What my intention was to show you is that core simulations do play a vital role in testing the actual systems. So these behaviors, what you get from our core simulation, processor and loop core simulations, they will be as close to the actual systems result. So with that note, I'll come back to the presentation. I would like to end come back to the end of my presentation to say a few things. It might be interesting. I'm not sure. It might. Let us see. Now, if you look into the information present in this slide, so this shows according to an estimate. So this shows the cost breakdown of implementing a microgrid project. So if you see very carefully, the equipment and installation cost is a major part of the microgrid project. It amounts to almost a 75%, and the remaining 15% goes to construction management. And see the last one, the 10% of one, which is going to the design engine engineering. So we don't have much of a provision to play with the installation. Unless and otherwise we are procuring the installations, we are doing a consulting work for installing, we are putting everything together. Unless we do that, as academicians I'm telling, we may not benefit from this 75%. The same thing, construction, building, all those things. Once again, these people will be taking care of this also. So we don't have much scope there also, unless and otherwise we have a way of consulting for installation and probably maintaining and taking it forward. We don't have much provision here, but we can look for we can eye for this 10% where we can play an important role as a consultant for the design aspects, and of course solving the issues which might pop up once in a while. That 10% we do can eye on. This is a very interesting part. If I show you the next slide, probably you will be all lightened up. Lighted up. I'll go to the next slide. Yes, the Indian microgrid market size was estimated as 2.38 billion US dollars in the last year. So that I think 2.38 billion dollars, something in the order of thousands of crores. I am not sure exactly. Now, and also they are projecting that this particular figure is going to grow at a, say, compounded annual growth rate of 19.4%, close to 20%. So which is another incentive, attractive thing. So assume if you are able to tap the 10% of this $2.38 billion approximately, if I'm not sure, once again, it might be coming in thousands of crores. So 10% of this thousands of crores, hundreds of crores. Okay, let us not go for hundreds of 10%. There might be n number of players. You just eye for 0.1% or 0.01%. You see where I'm going? So that is an incentive for us. We academicians, we don't have to stop with publishing, just publishing papers. You can take up your work to the next level also. So you can try to tap into this 10% also, which might be financially beneficial for us in many ways. In fact, professors from countries like the US, there I think they have around 2 to 3 days of vacation, which is not paid. So that is a time where they have to earn their own money. They won't get salaries from universities. That is a time where they, in full time manner, they do these kinds of consultant works. So if we are able to do a similar kind of work, we are in a sweet spot. That's what I want to say. Yes, and the another incentivizing thing or interesting thing is that this particular demand for microgrid is only going to increase as time passes on, and we do have getting very good support from the government. So all of these things should be of eating up a cake, should be of that much interest kindling things for us if we can properly make use of, tap on these informations and make use of it. And with that note, and this also, you can see this information. This is a number of Indian patents granted in selected renewable technologies. If you see the number of patents which are being granted is only going up and up, almost it is going up and up every year. I don't have the statistics beyond 2016. I hope it is continuing still. And most of these patents are I'm sorry, the power went out here. Most of these patents are held by the industrial people, the companies. And of course, there are a little bit of patents like what our IAC professors do hold. So that is another avenue. You can do your research, you can patent your research work technology, and then you can, of course, sell it for a handsome profit. So we have a number of possibilities available to take it up to the next level. It doesn't have to stop with just a publication of a paper. We can, of course, we can take it to the next level too. Just I thought of showing these things. Probably I'll thank you for your time. And I'd like to once again put it on record to thank the organizers for giving me an opportunity to present my views on and my knowledge, to share my knowledge in this faculty development program.
Thank you so much, sir, for your wonderful session. Before we get into the question and answer session, I just request all the participants to switch on their videos we would like to take a screenshot of this session. All the participants, kindly switch on your videos.
Kumaran sir, you please switch on the video, sir.
Sir, there is a power outage here.
Okay, sir. Okay.
I'll try to switch on my LED lamp.
Yes, sir. Chepana.
Is it better, sir, now?
Yes, sir. Yes, it's better, sir.
Okay.
Thank you so much, all the participants. Now I request the participants to raise their questions to our speaker. Kindly unmute yourself and you can speak.
So in the chat box, I see a couple of questions. If I miss any question, please one of you read it out. I think we can monitor system behavior, anomalies, and trigger. It's cyber attacks. We won't be able to incorporate it effectively here. So that is a function of advanced controllers. So what we are talking about is the localized controllers. Of course, these can be processed by our centralized controllers. Usually, we will have SCADA-like systems which are running on personal computer kind of things, computers. So of course, using these things, we might be able to handle that. I'm not very sure about cyber security, but in fact, this is one of the important aspect cyber security when it comes to microgrids. But I don't have answer regarding that. So if I have missed any questions, you can just unmute yourself and you can ask it. So there is another question. In what scenarios would a hybrid microgrid system combining multiple renewable sources be more advantageous than a single source? How would you optimize the energy mix in such a hybrid system? It's a good one. Of course, we know the vagaries of the power generated by our different renewable energy sources. For instance, if it is solar, we might not be able to get it during the night time. If there is no power, we won't be able to generate it during the periods when we don't have wind. So obviously we have to go for a mix of these kinds of renewable systems, and always in these microgrid systems we will see one DR at least, which is gas or a coal or a diesel based, not coal, a diesel based things, which is being as a backup to take up on that. And we do have the battery energy storage also processed by inverters to take care of situations like these. I hope I have answered that as well. Okay, don't see anything else. If you have any further queries, you can always reach me out in this email ID. And if it is a working day, I should respond you within one working day. If it is a holiday, in the next working day, I might respond to you. And thank you for such a lovely session.
Thank you so much, sir, for your wonderful session on the role of embedded controllers microgrids. Thank you for giving a beautiful insight on the topics you have covered, like microgrids, smart grid, power converters and controllers, embedded controllers. And also, I would like to appreciate you, sir, for sharing the simulation and modeling of uh, um, simulation software. Thank you so much, sir.
Thank you,
Dear
madam.
Thank you, sir. Dear participants, I will be sharing the feedback link of session 1. Kindly fill the feedback link. Uh, I'm sharing the feedback link in the chat group and also in the WhatsApp group. I request all the participants to kindly fill the feedback for session 1.
Kishore sir, I'm exiting the session. My UPS is almost down.
Yes,
Maybe
sir.
in 1 or 2 minutes it may go off.
Thank you, sir. Thank you so much for your great session. You have
Thank you,
shown,
sir.
as madam said, you have shown simulations also. As you have promised, you have shown simulations. Thank you so much, sir.
Thank you, sir. Thank you.
Yes, sir. Thank you, sir.
So session 1 is completed. We will be quickly moving on to session 2. We'll just take a break for 2 minutes. Kindly be online. We'll be starting session 2 in another 2 minutes. So kindly be online. Do not leave the session. Welcome, dear participant, for the second session, session 2, on the topic Role of Power Electronics in Renewable Energy System. This is the topic for the second session. The speaker for second session is Dr. V. Pushparajesh. Dr. Pushparajesh Vishwanathan, working as an working as a professor in Electrical and Electronics Engineering Department in JAIN deemed to be University, Bangalore. Has also the additional responsibility of faculty chair placements for JAIN University placements for past 5 years, that is from 2017 till date. He worked as an assistant professor, senior grade, in the Department of Electrical and Electronics Engineering at Congo Engineering College from June 2005 to 2017 for 12 years. He did his bachelor's degree in Electrical and Electronics Engineering from Bhartiar University, master's from Anna University, specialization in power electronics and drives, and a PhD in Electrical and Electronics Engineering from Anna University. He is having a total of 17 years of teaching experience in Electrical and Electronics Engineering at university, and he is guiding research scholars at doctorate level. He has received National Award in Engineering Excellence category as Best Placement Officer for the academic year 2019 to 2020 from ISIE India, and received Best Faculty Award for the year 2015 to 2016 at Congo Engineering College, India. He has guided 14 master degree holder students and published more than 23 high quality research papers in referred international journals like IEEE Explore, World Applied Science, and he has published 6 papers in national research journals. He has presented papers in 16 international conferences and 3 national conferences. He has written 4 books and monographs and has undertaken 11 consultancy projects. He has presented 12 sessions on the latest research topics in invited talks, FDP sessions, presentations, and keynote addresses and workshops. He has organized more than 22 training programs, STTP, summer school, seminar, workshop, industrial and special training programs. He has received funds from AICTE worth 6,60,000 for the Power Electronics Laboratory in MODROB scheme in the academic year 2012-2013. He is instrumental in industry institute activities in the form of MOU, industrial training courses, etc. We welcome you, sir. So I hand over the session to Dr. V. Pushparajesh for the second session. Welcome, sir.
Thank you, ma'am. Thank you for your introduction. So since there is a huge unstable in the network, so I'm just turning on my video and start with the audio session with all your permission. The topic that has been mentioned here, the role of power electronics and renewable energy system. The term power electronics and the term renewable energy, if you see both the terms, they are directly related with each other. They are purely dependent on each other. Power electronics is one terminology and renewable energy is another terminology. You can see power, electronics, energy. So all are correlated, all are interlinked with each other. So that is the reason why this specific topic has been chosen. Make the participants to understand, as we are from engineering, from electrical engineering background. From the day we start learning about electronics, then after a certain period of time, there comes the word power. So we are concentrating on the power electronics. So the power electronics, along with the renewable energy, is a ruling major part of energy sectors in our day-to-day life. That is why the specific topic has been given. I'll just start presenting my slide. So I hope my screen is visible.
Yes, sir, it's visible.
Yeah, thank you. So the basic outline of my presentation is, I'm just going to describe about a small introduction about what is a renewable energy and what is a renewable energy system, why we want to go for a renewable energy system, followed by what is a power electronics, what is the need of power electronics in renewable energy. And here, when I'm talking about renewable energy, the major thing which I thought, which is very important in our day-to-day life, which commonly we are start using either domestically or it will be commercially. Mainly, we are depending on solar and wind, which is the major constraint. At the later stage, even though we are talking about power electronics, renewable sources, there should be something behind which is used as an alternative sources of energy for storing the energy, whatever it is generated, nothing but the battery. So when you talk about the battery, again, it can be of different forms. It can be of different forms. Here I am trying to showcase two types of batteries. One is which is commonly used. One is your fuel cell. Another one is the flywheel, which is having better efficiency. And finally, when you're talking about power electronics, what you call as renewable, and what will be the load? Where this power electronics along with the renewable energy, what is the load we are going to connect and what is the outcome of the entire system is where I'm planning to talk something related to the charging infrastructure. Why the charging infrastructure has came into picture is as EV, electrical vehicle, is the current boom in the entire world. So, and when you talk about India, specifically India, because of this charging infrastructure, still we are lagging behind the commercialization of the electrical vehicle. So to give you a small glimpse about the infrastructure and how the power electronics and the renewable energy plays a major role in the charging infrastructure. So I thought of giving a small glimpse about those also. So this is how my entire presentation is lined up.
Sir, your screen is not visible, sir.
Ma'am, the screen is not moving.
Not visible, sir.
Tripti ma'am?
Sir, it's visible, sir.
Madam is
Sir,
in
it's
mute.
visible.
Okay, okay.
It's
Thank
visible,
you.
sir.
Okay, thank you, ma'am. Thank you. Yeah.
It is visible. What happened?
So first we will see the type of energy sources which is commonly we are as the basic thing. The participants to kindly mute yourself. Thank you for your quick response. So when you talk about the energy, normally we are calling it as a conventional energy sources and renewables energy, so or we can call it as a non-conventional and renewable. Where comes this differentiation? Where comes this differentiation of conventional and the non-conventional energy sources? So initially, even before the human being thought about the sun, wind, or biomass or whatever the natural things, there is a need of energy. There is a need of sector. Even though we started with the what you call as a small stones which will help us to catch the fire to make the light. Then slowly we are going for different levels. So when during the era of starting the light, they need some resources for generating the power. So there comes the initial generation of power using the thermal. You know, in India, most of the power is generated by thermal. Yes, we are already having so much of power. We can able to generate the power with the thermal. Why want to think about an alternative source? The reason is quite simple. Any source, if it is available in abundance, we don't want to worry about all the other things. We don't want to worry about any alternative. When we find there is a sudden drop in the sources available, obviously we thought of going for an alternative. There occurs the terminology, there occurs the word renewable has came into picture. Because the coal, when you start going on digging, it also having its own lifetime. It's also is having own depth, how much we can have it. So once we increase, go on increasing, taking it start depleting. Either it may be a nuclear, or it may be a thermal, or it may be whatever may be the resources we are using in the form of conventional mode, it start depleting. Even though it is depleting, but still majority of the power generated in the world is mainly through the thermal power plant. On the other side, the researchers, the people start thinking what will be the alternative source. As to one side it is going down, after a certain period of time, what will be our situation, where we are going to stand. There comes the person try to find out something is coming, something we want to think. There comes the man find the word renewable. So the renewable, as I told you, it is an alternative sources of energy of the conventional sources, but the usage or the limitation of renewable energy sources, again it's a limited one. This is in terms of the initial thoughts that came into mind between the conventional and non-conventional energy sources. On the other side, what are the drawbacks in both the sides? The major drawback when you go for the conventional is the pollution. The pollution. Part of the pollutions which is created either by petrol, diesel, by transmission mode or by generation mode, major part of the pollutants will come. We are all talking about greenhouse gases. But when you talk about the renewable energy, it is called as green energy. It does not create any pollution. The pollution level is zero when you're trying to match up the renewable energy sources. So based upon these constraints, the people start thinking of the renewable energy. And the basic renewable energy, what is a renewable energy system? What is a system? It is the combination of different renewable energy sources. Or we can call it as hybrid renewable energy sources. When you talk about hybrid, the majority of the researchers, majority of the papers which you are going, when they talk about hybrid, they mainly concentrate on the solar and the wind. The reason behind it is the availability of resource. Why? You can also think, why can't we go for a biogas or biomass? Yes, you can go, but it is available at a specific location. The cities like Bangalore, you cannot able to find that much of biogas plants because of the non-availability of the resources. So the major constraint that the renewable energy is dependent upon the solar and the wind. Fine. These are the two major hybrid sources which can be utilized to satisfy certain amount of global energy requirement. Though we are happy with using the renewable energy sources, on the other side, we should also think about the challenges that we are facing when you are going for the renewable energy sources. These things we will discuss in the upcoming slides. Why renewable energy sources? As I told you in the first slide, one is the clean and green energy which can be obtained by using renewable energy. The second thing is you can able to see the thermal energy, whatever you are using, you cannot use it to regenerate, or it cannot be used for regeneration. But when you use in hydro, which is again a renewable energy sources, can be reused for generating the power. So renewable energy sources can be reused. Certain renewable energy sources can be reused. And if you want to carry the energy, it is quite possible by means of using the power electronic devices to transfer over a long distance. That is the reason why renewable energy source, why the people are more dependent on the renewable energy sources compared to the conventional energy sources. I just want to tell you regarding the global renewable energy changes. See, as you saw in the slide, there will be huge variation of installation of renewable energy things. And you can see in the chart, almost 60% of the energy is obtained from the solar energy. Is obtained from the solar energy. For your kind information, as of 2024, the total amount of energy generated or power generated from renewable energy is almost 3,865 gigawatts. And there is a considerable increase in the amount of renewable energy power from 2022 onwards. From 2022, almost 476 gigawatts power has been generated. From 22 to this 24, almost 476. So the entire world is moving through the renewable energy. They found there is a huge gain can be obtained from the renewable energy sources. So the people, most of the power, it may be a private industry or it may be a government in the government sectors. They are trying to utilize more amount of renewable energy for meeting the demand. The other things of renewable energy you can see here is wind, which is almost 20 to 30%. Other than that, you can see geothermal, bioenergy. So these are some of the other what you call as non-renewable energy sources, but their contribution is only 2 to 3% and 3 to 5%. What about the energy in India? What about the renewable energy in India? This is the table I have taken from MNRE, the recent guide which has been published or given out by them. Here also, you can see the amount of energy determined by the non-conventional energy sources and the amount of energy that is recovered by the renewable energy. You can see in the table, it's clearly visible. The total amount of power generated is maximum in the non-renewable energy sources compared to renewable energy sources. Still, the renewable energy sources will have a good impact. Will provide a suitable partial contribution towards the total energy production in India. As per 2024 survey, the total amount of energy generated through renewable energy reached 200 gigawatts in India. In the 200 gigawatts, the solar will be almost 91 gigawatts. The wind is around 47.36 gigawatts. The hydro is again in line with your wind, because you know that more amount of water resources are there here and there. So it will also contributing almost 46 gigawatts. And biogas, we are having only 11 gigawatts. So this is what the energy level, this is what the power generation because of the renewable energy in India. In the statistics, you can see almost majority of the power contribution is only from the solar energy. Next come the power electronics. Why power electronics? As I told you, renewable energy and power electronics has to handshake with each other to meet the required demand. Renewable energy alone cannot operate in a standstill mode. Again, simply if you are using a power electronic device without renewable energy, there is no use. So both has to handshake with each other to provide or to meet the global energy demand. So as you know, power electronics is nothing but a semiconductor switch which is used to provide the required output or a controlled output whichever we require. It may be in terms of frequency, it may be in terms of speed, it may be in terms of torque, it may be in terms of power, whatever may be the output you require. It can be customized by using the power electronic devices. So these are, you can find certain type of applications where the major role of power electronics will be there. One is in hydropower, biomass, geothermal, solar photovoltaic, wind and tidal waves. So all these renewable energy sources, you can find there will be a considerable contribution of power electronic circuits in getting the proper required output from the renewable energy sources. First type which will comes into mind when you talk about the renewable energy is the solar energy system. What is a solar energy system? Solar energy system is a system which comprises of a solar photovoltaic cell followed by a power electronic circuits and a battery for storing the energy. As Kumaresan sir previous sessions told, you cannot, why need a battery for a solar energy or a solar photovoltaic cell? Because you cannot have the sun during the night time. But I want my energy, I want to place my energy. So what I do is I will use my battery for storing the solar energy. Okay. And when I talk about the solar panel is nothing but the combination of solar cells which may be connected either in series or parallel mode to form a PV array. Based upon the requirement, they will design, they will calculate the power requirement, and based upon that they will go for the solar panel. Along with the solar panel, as I told you, we will have the power electronic circuits. Normally when we talk about the power electronic circuits, there are different types of circuits. What we are calling it as a cathode, we are calling it as a converter, we are calling it as an inverter, sometimes we are calling it as a cycloconverter. So we are having n number of power electronic circuits. But in the case of solar and wind, the converter and inverters will play a major role to regulate the output based upon the needed things, based upon needed things. And in the case of solar energy system, there is one more terminology which people always think that is called as a charge controller. What is a charge controller? It's merely a controller. Which will operate on an algorithm, to effectively to maximum utilize of power from the solar panel, to maximum obtain the power from the solar panel. That is what called as a charge controller. So the basic types of solar panels, we are having the plain array of solar panels as well as we are having concentrated solar panels. When you talk about the applications of solar panels, the simple application which we are using in our houses is solar water heater. It is again, the structure of the solar water heater. The solar rays will play, you will have a black coated tube through which the water will be flowed and it will get heated. So solar energy, even you can go for solar cooking also. Solar energy will place a major contribution in our day-to-day life. So what will be the implementation of solar photovoltaic cell? So this is with respect to global scenario. I'm not able to get the global scenario of 2024. So I just took the global scenario of 714 gigawatts is the maximum, is the power generated from the solar panel as on 2020. Now, by 2020, that is until 2020, in 2020, we are having 127 gigawatts. See, what you can understand by seeing all those things is there is a huge demand, there is a huge contribution of solar panel in the near future. So solar, there are certain conditions will come where the entire power will be generated by the solar panel. So there is a huge solar panel installations are happening. You can see in India, a lot of solar parks start coming. Lot of huge solar parks start coming for generating the powers. Even government is giving a subsidy to install the rooftop panels in the apartments. It has to be self-sustained. They're asking the apartment to be self-sustained for meeting the demand of the entire apartment. So there are a lot of new schemes that government is coming out to make sure that the people are self-sustained in their energy. Along with that, we will have certain power. We are getting it from hydro also. We are having certain power. We are getting from hydro also. So total energy generated in India as on 2024 is 19.76 gigawatts. It's 19.76 gigawatts only in India. In the world, it is 714 gigawatts. In India, it is 90.76 gigawatts. What will be the structure of a photovoltaic system? As I told you, normally it is consists of photovoltaic cells. The photovoltaic cells are made up of single or polycrystal crystals. Now the recent technology, because these cells will have its own drawback. The solar panel will have its own drawback. What are the drawbacks which you can face when you're going for a solar panel? The major thing is shading of the solar panel, which will reduce the sun irradiation, that is the sliding on your solar panel. So you need huge maintenance. Proper maintenance of solar panel will help you to get the maximum power. That is one of the major drawbacks. Lot of research is still going on how to overcome the shading happening on your solar panel. And other than that, when rain comes, it again, the droplets on your solar panel will again create a proper slight changes in your output. So there are certain drawbacks also, but the material, that's why people now try to use new material for generating of the solar cells. People mainly work on the nano based solar energy cells to reduce the size of the solar panel and also to generate more power, to get more output efficient. You can see what are the different areas you can use the solar panel. And you, as I told you, the crystals which you are using in the solar panel can able to provide 14 to 20% of efficiency only. That's why lot of new materials, lot of researches are happening to design or to develop new materials for the design of solar cells so that the maximum efficiency can be obtained from the solar cells. So when you talk about the technology is nothing but what is the technique we are going to apply to get the maximum output. As I told you, you will have the solar photovoltaic cells. It may be in the form of different frames which consist of an array of cells. And the major thing which we are concentrating in this session is the that is power electronic circuits. As I told you, there are different types of power electronics. As I told you, one is a DC to DC converter, which we are calling it as a chopper in one case, or can also be called as a DC transformer. Okay, why it is called as a DC transformer? Chopper can be, because normally when you talk about the transformer, we are talking about step up and step down. Similarly, in the chopper, it can also be step up the voltage, as it can also step down the voltage. That's why choppers are normally DC to DC converters are normally called as a DC transformers. When you go for the other side, the inverter, you know that the output of your solar panel, it's purely a DC output. And usually what happens when you talk about the operation of your solar panel, what we'll do is the output will be boosted up. And then the output, when you want to connect it with the grid, if you want to connect it directly to your DC motor application, you can directly use it. Or if you want to go for any AC applications, for example, you want to drive any AC motor, or you want to drive any, or you want to connect to any grid, then obviously you need another special power electronic circuit called as an inverter. So inverter and converter are the two major backbones of power electronics. So you'll convert your DC into AC, and then it is connected to the grid. And there will be, when you connect it to the grid, you want to see the frequency matching, sub-synchronization should be done. It should be synchronized with the frequency of the grid before connecting to the grid. There will be a lot of frequency mismatching will be happen. All these things has to be considered by means of the power electronic circuits. And a small diagram I am showing you how a rooftop solar panel is installed and what are the other devices, as I told you, charge controller, inverter, converter, which are installed such that the required power can be obtained and connected with the grid. So as I told you, the major requirements we saw, it is inverter and converter on the solar panel. Other than that, there is something what we talk about, the control algorithm or the controller. So when you talk about the controller, particularly in the case of solar panel, many of the researchers does not forget to touch the algorithm, touch the topic or the terminology MPPT. It is maximum power point tracking. This is the first algorithm any researcher who is interested to work on solar panel will touch this terminology when you go when you go for the control technique. When you want to apply a control technique, this is the first terminology he is touching. So MPPT is nothing but tracking. You are using the solar panel to track the maximum power to get the maximum output. So tracking the irradiation and find out the maximum irradiation and provided the maximum output. That is what is called as a MPPT. It's mere an algorithm. It's mere a control algorithm. Other than that, you will have the power electronic circuits which we have, which is normally used to produce a reliable, efficient, controllable output that can be connected with the grid. And when you're going for a grid, you should be very careful about the quality of your power and your voltage level, your frequency level, and you also understand is there any fault right through. So you will have solar panel side, you will have the power electronic circuit. Whatever the circuit you are using, it should be highly efficient one. And also, since you are using switches, let us consider either it may be go for IGBT or it may be a MOSFET. What is the type of switches you are having? The thermal management is something which you should be very careful, because certain cases, what is the problem is when you are using these type of switches, there is a problem of the harmonics. There is a problem of harmonics. When you talk about the AC side, there is a problem of torque ripples. When you are talking about the what you call this, your DC side, the problem here is these harmonics will act as a source and it will inject its content towards your source, which will cause a huge failure in the source side as well as in the load side also. So always the operating of your power electronic devices should be very carefully operated. Okay, even though we are using a PWM signal to pulse width modulation technique to provide the gating pulse for the power electronic circuit, care should be taken based upon the novelty of the devices, based upon the sources and the load what you are connected in the circuit. And if you operate the energy within switching frequency for say as XZ, you should know what is the generation of harmonics there. We are calling in other terminologies THD, total harmonic distortions. So in the previous presentation, Sarah has told, as per the IEEE standard, the current harmonics and voltage harmonics are the two major constraints here. The voltage harmonics, even though the voltage we are trying to keep the voltage level at a constant one, at the constant level. So the voltage harmonics are allowed to go up to 8%, but whereas in the case of current, it should be minimum, it should be less than 5%. So care should be taken in the case when you are operating your circuit with any nonlinear loads, care should be taken how you are operating your power electronic circuit. Then a simple inverter circuit configuration. You can see there are different types of inverter configuration. One is for a lower voltage, which is of 100 watts. You can have a simple module inverter, which is specified here, a simple inverter, the converter based circuit. When you are connecting with a grid, okay, the size of your converter, the size of the converter and the number of legs or the operational wise, it will be quite different, because when you connect with the grid, as I told you, there should be a difference in the frequency, there should be a different voltage level, everything has to be stabilized, everything has to be taken care. And that's why I told it may be a single phase supply, it may be a 3-phase supply. Based upon that, your inverter and the converter design has to be made. And third one is stringer or multi-string converter. See, these multi-string converters are nothing but the converters which is normally used for the higher voltages, higher voltages, or it will be normally used for the higher capacitor. Here, this will convert the solar panel output into an alternative one. It is an alternative one, and make the output very smoother. And it will make the output very smoother. In the case, it will make the output a pure sinusoidal, so that it can be connected with your grid directly. There is one more inverter which is called as a central inverter, where you can see the number of solar PV strings, and each output will be individually converted. Each strings will be connected or will be connected to the DC to DC, and it will be properly, individual strings will be connected, and output of individual strings is varied, is controlled, and then fed to the inverter. So each and every strings will be taken care separately. That is why it is called as a central one inverter, which will take off individual string of solar panel. In the case of multi-string, each string of solar panel will be taken pair by each strings of converter. So these are some type of inverters which can be used based upon the different levels of power, So this is a simple diagram where what is the effect? What is the effect? You can see a DC to AC inverter circuit here, and there should be a small DC to DC converter circuit here. Okay, this DC to DC converter will it is used. It is a 640 kilowatt three-phase circuit. You can see the three phases is mentioned as the output, which is connected to the grid. So you are using a small DC to DC converter for implementing the MPPT algorithm. In the circuit to obtain the maximum power from the solar panel. This is in terms of the generation side. And when you connect it to the grid, there are different configuration of power electronic circuits you can use. One is transformer-based grid configuration. In this transformer-based grid configuration, you can see the transformers with multiple stampings, which is used as an inverter, which is used as a grid converter inverter to produce a pure sinusoidal output, which can be connected with the grid. Again, I am repeating, this is a form of power electronic circuit. We can see LF is nothing but the low frequency, HF is nothing but the high frequency transformer circuit. In this transformer circuit, these transformers will have a huge number of stampings, and it itself will act as an inverter. It itself will act as a grid connector inverter to produce a pure sinusoidal output to be connected with the grid. When you talk about the transformer-less grid, here we are not using any transformer-based inverter. Here we are going for the conventional mode of operation before connecting with the grid. These are a few inverters. I will just show a few more. This is AC module inverter. This is another universal AC module inverter, which you will have these switches here. You will have a rectifier. You will have diodes followed by a switch. Okay, followed by a switch, and on the other side you will have the inverter circuit, which is connected to the grid. So you will have the converter here. You will have the converter here, followed by the inverter here. You will have the converter here, followed by the inverter here before converting to the grid. This is of a single stage. That means each stage, individual stages, it will perform its operation and then go for the what you call as grid connected. You will have universal AC module, and you will have buck boost inverter, full bridge inverter. So you can see, as you all know, buck boost is nothing but the voltage can be either increased, or it can be the voltage level can be increased or decreased based upon the output from the solar panel. Based upon the output from the solar panel, the voltage level can be increased or the voltage level can be decreased. So that's why it is called as a buck boost integrated full bridge inverter. The next type of converter here is conventional normal DC to DC converter. and then you will have the flywheel disc optimizers. So these are some of the converters and inverters which can be used along with your solar PV panel to increase the or to optimize or to increase the power output that is fetting to the grid. And also you can find a lot of DC link, lots of filter circuits are there, a lot of DC link in what you call as inductors are there. These type of additional equipments, which are additional components which are available, they are normally used for filtering the distortions which is happening because of high switching devices, and all those things can be suppressed so that the output can be a steady state output which we are fitting to the grid. And this is a new type of inverter which is a multi-string. As I told you, when you are operating your when you want to record output is of 1 kilowatt to 30 kilowatt, obviously single or multi-string inverters are used. This multi-string inverter, as I told you, it will form as an inverter circuit, and it is used mainly in the houses. See, these inverter circuits, they are mainly used in the houses. The reason behind is the one is the voltage level. One is the voltage level, mainly is in the houses, and it can also be used in the commercials. You can see, you can have a different strings. So this is what is called as a strings. This is what is called as a single string, and you can have to multiple string. The major advantage of using this type of inverter is the efficiency. You can have the maximum efficiency of 95%. Then the other types of inverters, you'll have transformerless string inverter. It is also called as H5 transformerless inverter. It is nothing but a modified H-bridge inverter is called as an H5 transformerless inverter. And why the name H5? Why the name H5 is because it is using 5 switches. It is using 5 switches, and the switch which is available at the middle, which is shown here, the 5th switch. Sorry. This 5th switch is the switch which will be used for the operation, which will be used for the what you call as. Sorry, it will be the switch which is used to perform the maximum power point. It is used for providing the maximum power point, and this has been modified has been patented by the industry SMA. So that's why it is called as an H5 transformerless inverter, where there is no transformer here. Only the switch is help us to provide the maximum output by reducing the leakage current, okay, and also the losses will also be minimized because of the 5th switch. The next type of transformer is H6 transformerless inverter. It has been patented by the team called Inaugural team. That's why they given the name H6. Again, you can find how in the previous case you will have 5th switch. Here you will have 6 switches. Here you will have 6 switches. That means the voltage is divided by VDC by 2. In the previous case, it's a VD. Here it is a VDC by 2. And here this switch will provide much more reduced in the leakage current as well as the losses, as well as the conduction losses is also very, very minimum. So these type of switches can be used in the case when you find there will be any leakage currents, or any electronic field inferences will be there. In such cases, these type of H-bridge inverters. Now, many of the researchers are using this modified H-bridge inverter, particularly when they are working on the solar panel. There is the next type of inverter is the NPC, neutral point clamped converter, which is very commonly used by many of the researchers. Okay, the neutral power point, that is, you can see that there will be HD this link voltages will be there, which is greater than the grid peak voltages. Okay, so this is very commonly used inverter, particularly for the solar panel. When you have multiple modules of solar panels, you can go for the neutral point clamped inverter. The last one, what we are going to see is the central inverter. As I told you, when your power output is going beyond 30 kilowatt, when you are going in terms of megawatts, obviously you want to set up a new inverter, which is called as a central inverter, which is used normally in the case of large power plants. Okay, that is, as I told you, it is of 750 megawatts. Those type of power plants, we are going for this high switch speed inverters, high switching speed inverters, which is converted to the solar panel to convert the low voltage into a medium voltage, and then the medium voltage will be connected to the grid. Okay, and then medium voltage will be connected, or mega voltage will be connected to the grid. So low voltage is converted into mega voltage, and mega volt will be connected to the grid. That means high voltage can be connected to the grid. The general architecture of a solar panel, this is a closed loop system where your solar panel will be available, and then you will have the power electronic circuits. Normally the filters will be used to reduce the ripples if it is a DC side. If it is a AC side, it is used to reduce the harmonics because of the switching action of your power electronic circuits, and then you will connect it to the grid. So in the bottom there is a small box which helps you to understand what are the different types of algorithms. What are the different types of algorithms? What are the different types of things you should consider before feeding the power to the grid? Before feeding the power to the grid, you see that grid current, grid voltage, DC voltage, grid synchronization. As I told you, it's very, very important. And in terms of solar panel, you want to monitor your plant operation, the efficiency, because there is a possibility of a lot of malfunctions happen. Short circuit between two cells can be happen. So obviously it will collapse the entire solar panel operations, the array of solar panels. So care should be taken to determine, and also you want to give you a proper isolation circuit between each cells so that the short circuiting issues can be avoided. It should be done as per the IEEE standard. Okay, and you should know now what happens is, now these solar panels, they are using an advanced technique such that the solar panels can be turned, it can be moved based upon the sun rays. When during the morning the direction of sun is in one side, the solar panel will be projected towards the side. When the sun is moving from one side to another side, obviously based upon the radiation, amount of radiation, it will sense the rays, percentage of rays hitting on the solar panel. Then the solar panel will be automatically turned based on the direction of the sun. Okay, so this is with respect to the solar panel. With respect to the grid, as I told you, voltage control, frequency control, power quality, all those things you have to take care when you are connecting with the grid. And as I told you, MPPT is the basic algorithm. Any researcher who is working in solar panel will start using the panel. So this MPPT, as there are different types of MPPT algorithm. One is PNO, that is perturb and observe MPPT algorithm, which is very commonly used by the researchers when they are at the beginners. Other than that, you will have constant voltage, short current pulse, and ripple correlation control. These are the other MPPT algorithms can be used. And also I just specify for your understanding what are the advantages and what are the disadvantages of going for different types of MPPT algorithms. But make it clear, MPPT algorithm is the major algorithm where most of the researchers, they are trying to inculcate, along with the MPPT, they are trying to inculcate some of the AI technique like fuzzy logic or neural network or genetic algorithm or hybrid intelligent controller or hybrid AI control. They are trying to implement, they are trying to incorporate some of the AI control techniques along with the MPPT algorithm to optimize or to improve the MPPT algorithm so that the maximum power point by MPPT algorithm can be operated very effectively to get the maximum output. So this is a simple circuit where an MPPT algorithm can be obtained. So you can see this is where the MPPT algorithm, it will measure the current and the voltage, and the grid side is also measured, and based upon the analysis you can determine where the maximum power can be determined, it can be a single stage or it can be a double stage. Okay, it can be a single stage MPPT algorithm or it can be a double stage. The only thing is here the DC to DC converter is not available in the case of single stage. It will be available in the case of double stage to increase the voltage to a certain level. And usually, as I told you, power electronics is nothing but the switches. You can find the different types of switches, MOSFETs, super junction silicon MOSFET, CAN. And these are some of the power electronic switches which can be used in the power electronic circuits of solar PV panel, so that you can able to obtain the required output. Just for your understanding of different characteristics of each and every switches I have mentioned here. And when you are connecting the things to the grid, so there are certain codes you want to follow when you are connecting your photovoltaic cell to the grid. One is, as I told you, power quality, frequency, maximum active power capture. That means how much power you are going to capture, and the communication. The communication nothing but, as I told you, you can able to monitor your entire PowerPoint tracking using your mobile, which is fitting to the grid, and the efficiency. In case of if the power plant, if the PV is very bigger, it is operating, for example, 70 to 50 kilowatt or more, then the certain things you want to consider is reactive power control, frequency control, and fault drive-through capability. Okay, these are the things that you should consider in mind before connecting your PV output to your grid. So before going that, I will give a small example which happened, which I have thought of sharing with you. So in my home, I'm having 3 kilowatt demand in my home. So what happens is last 2-3 months before, suddenly I found there is a huge increase in the tariff, huge increase in the power consumption in my house. Then as an electrical engineer, we are also thought of thinking something, why suddenly there is a sudden increase in power. I just encountered with different people, including the electricity board. I just thought with them. They said one problem with them is, are you using an UPS? I said yes, we are using an UPS. When there is a malfunction in your UPS, the power will start to increase. As I told you, this malfunction of your inverter in your UPS will generate the harmonics, will act as an additional source. The harmonics results in the increasing of, because there will be a lot of leakages will be happening, results in the increases of our power requirement. Then obviously I also thought, and I just checked with the UPS and tried to find out, is there any problem? I found there is no problem. Then again they told, let me wait for 1 more month and then check. Then I thought, why can't we go as an electrical engineering? We are all teaching our students about solar, wind, and so many things. So I thought, okay, why can't we go for a PV panel, a solar PV? I have installed a solar PV of around a 2 kilowatt solar panel I have installed, and I just try to find out the energy consumption. What I try to done is, in the morning, during the morning hours, I try to utilize completely the solar panel, and even I don't even getting a battery, big battery for charging the solar energy is a little bit costly. So I gone for a normal small size of more battery. Then what I said is, only during the night time I try to use, that is only from night 9 o'clock to morning 6 o'clock, I try to use only the grid power. So what happens is, the 1 unit of solar power, it costs around 300 rupees, sorry, 3 rupees, 2.5 to 3, whereas the same thing with grid is around 6. So I found there will be considerable reduction of the power as well as the tariff. So now I'm start using, I feel very comfortable in using the hybrid sources from morning 6 to morning 9 to evening 9 with solar, and from the remaining period I will start using the grid. So it's a quite term, because what is the problem is, when you are using this solar panel, there is, you can avoid during the peak load period. What happens is, we are creating a huge impact on the grid because of the sudden increase in the peak load during the peak hour. So what I try to do is, because of the solar panel, there is no problem for me to have this peak load period, because the enough amount of solar energy which I stored in the battery can be used, because up to 5:30 to 6 we will have the solar energy considerably. So those period I will try to store into the battery, and during the evening hours I try to utilize it. That much the battery have the capability to use. So I found there is a big relief, and I found another 2 years maximum where I can get the payback period of installing the solar panel in our home. Okay, the only additional thing is this inverter converter circuits, and the algorithm is charge controller is the additional things which we have. But only thing is we have to maintain it properly. We have to see that there should not be any dust particles or any water droplets on the solar panel. Care should be taken. If you consider, if you take such cares in your houses, it can able to even water heater, everything can be operated using the solar panel. It's a small thing which I experienced. I thought of sharing with you. The next thing is wind energy. As you all know, wind energy is another sources of energy, but considerably the amount of power generated from the windmill is less. So what a wind energy system consider? A wind energy system consider a wind plant. Followed, the wind plant itself will consist of the blades. You will have the generator. You will have the what you call as gear arrangement, a drivetrain related arrangements, and then followed by a battery. So this is how a normal blade arrangement will be there. Here these blades are normally the blades can be operated initially. The blades cannot be operated as we like. Okay, the blade should be operated minimum with 12 to 14 km/h speed. Initially excitation has to be given for the blade to run at constant speed. There are some people say that when the wind is huge high, the blade will speed at higher speed. No, the blade cannot run at higher speed. If it run at higher speed, obviously it will get collapsed. So the blade always run at a constant speed, and whatever the wind energy inside the blade, inside the area, there should be some gear arrangement. Based upon the gear arrangement, you can have the required output. Here the problem here is the what you call as the operational cost, the construction cost or the installation cost is more in the case of wind plant, but the operational cost is very less. The operational cost is very less because you don't need that much of maintenance what we are having in the solar panel. Solar panel is just the vice versa. Their installation cost is less, but the operational cost is more. But here, installation cost is more, but the operational cost is less because you don't need that much of what you call as maintenance for your wind energy system. So again, as I told you, it will convert the kinetic energy into mechanical output, and then mechanical power is again converted into electricity using a generator. So initially, the people start using the induction generator. Okay, so for initial excitation, they used as a motor for initial excitation. Once it gets initial excitation, then they using it as a generator for generating the required output. So initially they used the induction generator motor as a generator. After that, they start going for a synchronous generator. Currently, recent research, they are going for permanent magnet brushless DC motor, PMBLDC. Okay, our permanent magnet DC motor. And then they are going for the switch reluctance DC motors, switch reluctance motor and generator because of its high efficiency, high torque. Anyway, we are using a power electronic circuits there. So along with this, we can use the special electrical machines to generate more required output so that there is to avoid the pollution as well as the clean energy can be obtained. So when you talk about the availability of what you call as wind energy, so it will be around 733 gigawatts, and in the year 2020 it will be 111 gigawatts. It will be 111 gigawatts. So in India, the total energy generated by the wind yes on 2024 is around 47.63 gigawatts, 43.63 gigawatts, and it is increasing. You can find a lot of solar plants, lot of wind energy plants are coming in the market, for generation of the power. So you can get more number of energy sources. You can get more number of energy sources in the market. You can get up more number of energy sources in the market. The next one is wind turbine technologies. As I told you, the technology began the wind turbine. As I told you, there is again the power electronic circuit will plays a major role. Again, see the input is an, the output of a wind turbine is an AC. So the AC is converted into DC by means of a rectifier or a converter circuit, and then after boosting the voltage level based on the required level, it will be again converted into AC before fitting into the grid. Initially, they are gone for very low installation of the wind plants. Say as in 1980s, 50 kilowatt wind turbines are installed, but recently you can see there are maximum of, they are going up to 10 megawatts wind plant they are installing to get the required output for the various applications. So as I told you, you can see inside, you can have a wind, what you call as gear arrangements followed by a generator, and then followed by a generator, and then output will be, you're taking the output and storing it in the battery. Battery will be at the downside, battery will be outside. This is the top view of your blade, top view of the structure of your blade. And as I told you, it will have a generator. The major requirement, you will have a generator to generate the required output from a mechanical to an electrical. And when you talk about the power electronic circuits which you are using as an converter and as an inverter, the whatever the transformation you are doing, these devices should able to provide a balanced output, and it should able to provide high power density as well as the better reliability should be there. When you're talking about the grid output, when you're connecting it, it should be controllable. It should provide a proper response, proper frequency matching, proper voltage matching. Everything should be maintained before connecting to the grid. So when you talk about the grid, as you said, DFIG is one of the what you call as drive which we are using. Double field induction generator. It is one of the currently many of the windmill they are using this generator setup for the power generation. So here you can find a gearbox will be there, and slip rings will be there. Again, as I told you, when you want to increase the speed, when you increase the slip, obviously the speed will also increase. That means in terms of the motor generator setup, you will have the power converters, as I told you, DC to AC, and then again, sorry, AC to DC, and again DC is again converted into AC. So in the case of full scale with SG, synchronous generator, the first diagram you can see double field induction generator can be used. In the second things you can call it, you see synchronous generator or permanent magnet generator can be used, where you can see the variation in the usage of power electronic circuit. Here it will be a partial one. Here with the help of the filter, you are using the filter both in the source side as well as the load side. As I told you, the power electronic circuits will have the capability of injecting the power back to the grid, back to the source. So there will be a filter circuit for filtering the unwanted or for reducing the unwanted ripples or harmonics spreading back to the source of the load. Then this is at the generator side. Okay, it is at the generator side. Power generator, you will have the gearbox for generating it. And you can see the frequency, the variation of the frequency can be taken care by the power electronic circuit. The variation of the power and frequency can be converted by using the power electronic circuits before fitting into the grid, before fitting into this grid. So there also, these power electronics will play a major role. And this is with respect to the plant side, that is with respect to the generator wind turbine side. This is for to generator, and make sure these plants should be located in such a way the required amount of wind should be available. Otherwise, simply exciting your wind blade does not yield any impact for you. And there is a new advanced technology which I'm showing in the next slide, sir, not this. So you can see here, by means of varying the slip, of the circuit of the motor or the generator which is available, you can able to get the required output. By varying the slip, the output can also be varied. Here you can see 1% of the slip, 10% of the slip, 30% and 100%. When you go to vary, you can see the usage of different power electronic circuits. With up to 10% of the circuit, you can have a cascaded, you can have a cascaded what you call as power electronic circuit, which can be used as a soft starter. When you go for higher end slip, where your frequency, voltage or the power will plays a major role, you can use a separator, inverter, converter bar circuit. You can use a separator, inverter and converter bar circuits. And this is the general structure of wind turbine system, as I told you. So it is your drive system will be available here, and these are the power electronic circuits similar to our PV panel, and these are some of the algorithms. In wind energy also you can go for n number of algorithms. Even there is something called as a maximum wind energy tracking system. Even here also the wind blades can be turned, the entire part of the wind, the top part of your wind plant can be rotated based upon the direction of the wind. Above the front part up can be rotated based upon the direction of the anemometer, which is used to calculate the wind speed, will help you to determine the direction at which wind is blowing at the higher direction. You can rotate your wind plant so that maximum power can be generated from the wind. So here also, when you're connecting your grid to the what you call as wind turbine, here also certain things can be followed. One is power can be active power, reactive power, frequency, steady state operation. These are the certain things you should keep in your mind when you are connecting your wind with the grid. And this is a small MATLAB. This is a small MATLAB circuit which used permanent magnet synchronous generator based wind system. So you can see PMSGM, and these are some of the controllers and the converter circuits. For getting the maximum output in the PMSG. These are some of the power electronic circuits. You can see IGBT devices and then MOSFETs. You can see the IGBT devices. See, maximum in the case of PV, maximum circuits will be designed using MOSFET. But when you talk about the solar, the wind power plant, the maximum circuits they are using with IGBT, because the high switching frequency of IGBT and fast switching speed is mandatory when you are going for the wind energy conversion system. The next thing, as we saw what is renewable, we saw what is solar, we saw what is power electronics tool, we saw what is okay. What is the final outcome where we are going to use it when it is not there? There is where the word comes, battery energy storage system. Battery energy storage system, again, how the energy can be stored in the battery, how the energy can be retrieved from the battery, how you are charging your battery, how the battery can be charged, how the battery can be discharged, is again in the hands of power electronic devices. It's again in the hands of power electronic devices. By making a clear D, we are normally calling this a delta or delta D, which we are calling it as a angle, duty cycle or duty angle for charging your battery, will increase the lifespan of your battery also. You know that every battery will have a certain life cycles, says 5,000 cycles or 8,000 cycles. Cycle is nothing but charging and discharging will be considered of one cycle. So what happens is there are certain things where we are charging our battery just like that. So when you go on charging your battery at a different voltage levels, instead of maintaining it at a constant voltage, if you're just charging your battery, obviously the battery lifetime will start to reduce. Obviously, the battery lifetime will start to reduce. So make sure whatever the battery you are using, it should be properly charged. Rate of charging should be proper and rate of discharging should be proper. And again, charging and discharging will be, it is in the hand of the power electronic circuits what you are using for charging your battery. As I told you, these power electronics will play a major role in charging your battery as well as in discharge. The rate of charging of your battery, rate of discharging of your battery, again depends upon the power electronic circuits what you are adopting. See, you can see the power electronics, as I told you, the power electronic circuits. This circuit will decide what is the rate you are charging in your battery. It may be lithium ion, or it may be nickel cadmium, or it may be any ferromagnetic battery, whatever may be the battery. The battery healthiness is purely based upon the state of charge and state of discharge. And the state of charge and state of discharge is again purely depends upon your power electronic circuits. It purely depends upon your power electronic circuits. This is another. This is in the case of your fuel cell, for example, a hydrogen fuel cell based battery. This is our conventional battery, like a lithium ion battery or nickel cadmium battery, whatever may be. Both the cases you need the proper power electronic circuits. Since battery is purely a DC, so you should have a proper voltage stabilization before steady state, making the voltage in a steady state, and you have to reduce all the ripples and everything before storing it in the batteries. So the other types of energy storage systems are fuel cell energy storage system. Again, when you are using a fuel cell energy storage system, you need a proper power electronic circuits. The another energy storage is fuel cell. In both the energy storage system, this is a little bit advanced and more efficient compared to the conventional battery. But again, here also you need a proper power electronic circuit for determining the state of charge and the state of discharge, so that the efficiency of your battery, or maybe flywheel, or maybe ultra capacitor battery, whatever it may be, it can be improved. Okay. So the next type of energy storage, this is a new energy storage, superconducting magnetic energy. It is nothing but a floppy disk, or you can call this what you call as two magnetic coils through which the energy can be stored. The energy can be stored, and here you can utilize the energy, but here the amount of requirement of storing of energy is not up to the level. It's only a minimum amount energy can be stored, and it can be used efficiently whenever it is needed. And this is something new, power to gas. Your power can be converted into gas and then it is stored. Converted into hydrogen or natural gas, and it can be stored in a P2G system. And whenever you need this, gas is again converted into power and can be used for an application. Okay, this is in this case also we are using the power electronic circuits for performing its operations. The last topic which I am planning to start is the bidirectional EV charging stations. Again, either it is a renewable or power electronics, there should be some load to be connected. Grid is, we cannot consider the grid as a major role. I'm talking load in some applications where we want, that is where these charging stations. As you know, EV is the upcoming, EV is the major part of vehicles everybody is talking about. And you know, by 2030, almost 60 countries are signed an agreement that they are going to completely convert their conventional vehicle into EV vehicle. When everybody start converting the conventional vehicle into EV vehicle, the major problem arises is the charging stations. Where we can find that much of charging station? And again, you need huge amount of power to be generated so that it can satisfy, or it can be fed to the charging stations, satisfy that to charge the EVs. So there comes this renewable energy. The renewable energy will be used as a additional, along with the grid, it can be used as an additional resources provide for the charging station for charging the EV. Why I specifically used bidirectional EV is even in the charging of an electrical vehicle, you need a power electronic circuit. You need a power electronic circuit. If you take Tata Nexon or Mitsubishi Canter, whatever may be the EV you are using, each EV, the manufacturer have designed their charging in a very customized way. So that's why people have started working on the universal charger, so that any vehicle can be charged. Anybody can go to any charging station to charge their vehicle. So they are trying to find a universal charger for all types of EV so that their vehicle can be charged in any station in any part of the world. Okay, so charging station, as I'm trying to say, what I'm trying to do is I'm connecting my renewable energy along with my charging station with the help of power electronic circuits so that the charging station can be efficient. Why bidirectional? Why I'm telling it is a bidirectional is not only the vehicle can be charged, and also the charged vehicle can be used to charge an additional things. Here we are calling it as a vehicle to grid. Not only you are charging your vehicle from the grid, again if your grid has charged, your vehicle has charged and you are not using the vehicle for another 2 days, the power will be there. So what I can do is I will make my power to the grid. That is something what we are calling it as privately people are doing it as a power trading. It's nothing but power trading, where you can trade the power which you earned, which you generated more back to the grid, and you can earn based on the things. The next one is vehicle to home. I hope you saw the movie of 3 Idiots, okay, where in the marriage, when there is a sudden power goes, what happens is the hero will connect all the batteries. He will take out all the batteries, connected all the batteries, and make the house and energize the entire building. That is what is called as a vehicle to home. If you don't have power in your house, you can use your EV. The battery can be used along with the power electronic circuit to charge your home. Your home can be energized. Your home can be charged by using a vehicle. That is why I said you need a bidirectional charger. Bidirectional. To charge your vehicle from your home or your home to the vehicle, you need a bidirectional charge. The third one is the vehicle to load. Any additional loads like street lamps. In your street lamps are not glowing, use your vehicle to connect the street lamps. That is called as a load. And last one is the vehicle. Conventionally, we are doing when your vehicle battery goes low, we are bringing another vehicle to charge your battery. So these are some of the uses of bidirectional chargers. I'll show you a small diagram. Vehicle to grid, vehicle to load, vehicle to home, and vehicle to vehicle. See, in the case of vehicle to home, vehicle to grid, you can adapt the renewable energy to install a better charging station where the impact of grid is lesser because the charging will be taken care by solar panel. So lot of research are going on in few of the foreign countries. The top layer of the bunk charging stations are completely embedded with the solar panel, and whatever the power generated in the solar panel, they are using part of the power for charging the EV. So these are some of the advantages: money, backup power. It may be used as a portable power source. The another topic which is commonly discussed by many of the people is wireless power transfer. The countries like Italy, Israel, Denmark, Australia, few countries they started using this wireless power transfer. What is wireless power transfer? It is nothing but the transferring the power wirelessly between two devices, and this concept now people are following mostly for the electrical vehicle. I'll just show you the diagram. This is how the power flow. You should have a transmitter, you should have a receiver. The transmitter will be in the ground or in the road, the receiver in the vehicle. So when the vehicle move towards the transmitter, when the vehicle receiver is in line with the transmitter, there will be a transmitting of power. Again, when the power is transmitting, the power conditioning, battery storage, all those things, again, the role of power electronics will plays a major role. You can see in this diagram, DC power connected to grid, DC to DC converter. You are having a rectifier. So without any power electronics, even wireless charging is also not possible. So the major components of wireless charging here is you will have the rectifier on one side is a transmitter which is in the ground, other side in the receiver which is on the vehicle. This is the area where your power is transmitted from your source to load or from your transmitter to receiver. You can see in both the sides you will have the inverter, converter. The entire power electronic circuits will play a major role. So a simple diagram which will shows the charging system and what are the various areas where your power electronics plays a major role. In the appliances, even in our domestic appliances, the power electronics will play a major role. In PV, in the case of residential, in the case of power distribution industry, in the case of automobile, in transportations, in wind turbine, everywhere the role of power electronics will play a major role when increasing the size of the plants. And the last slide, I thought of giving a small glimpse for the faculties who are going to start their research. So the first area in renewable energy is one is PV panel design, particularly with respect to the materials used for design the solar cells as well as the solar array. Then the next one is the inverter and converter. N number of inverters, N number of converters are there. The peoples are using what you call as hybrid inverter converter mode. They are using. A lot of peoples are now going for the multi-level inverters up to different levels. They are using to make the output very smoother. So that is second part where many of them are doing the research. Third one is the drives. Drives is nothing but instead of induction generator, you can go for, as I told you, permanent magnet synchronous motor, or maybe you can go for switch reluctance motor. A lot of special electrical machines can be used in the wind energy conversion system to make the system more efficient. And the next one is the microgrid. Microgrid is nothing but an islanded microgrid where your solar and wind will be a part of that microgrid. And without creating major impact on our regular grid, you can provide or you can energize a small locality of the houses with the help of your microgrid concept. Okay. And wind blade structure, again, this is a mechanical part where the wind blade design with materials can be used to get the maximum power output, to get the maximum kinetic output. Then drivetrain is nothing but the power transmitting media along with the generator and the gear shaft arrangement. There also a lot of people are working to efficiently use the drivetrain technology so that the required power can be obtained. And materials for the battery, you all know battery is the cost of the battery is increasing day by day, and also the life cycle of the battery is also decreasing day by day. Lot of researchers are working to determine the material. Now recently the industries like Toyota or industries like L&T, they are start using this sodium, conventionally using sodium material for designing the electrolyte to reduce the cost of the battery. And last one is the controller design. People are using AI, people are using ML. Lot of new controllers with new algorithms are coming in day to day, and hybriding this algorithm with hybriding these controllers with different types of control techniques like sliding mode controller, field orientation controller, direct or control technique with for the solar panel or wind will produce a good results. These are some of the areas who are doing research, who are going to start the research. Kindly think it of these areas where a lot of people are working and a lot of areas are there to cover for you. So this is my small suggestions. And when you want to get more data with respect to solar and wind, there are two agencies. One is National Institute of Solar Energy and National Institute of Wind Energy, where major amount of research particular to different types of solar panels, materials are happening, and different types of blade, different heights, vertical wind blade, horizontal wind blade. Lot of researchers are happening in these two, and you can able to connect them to get real-time data for your further research. So the final conclusion is there is no independent terminologies: solar, wind, renewable, power electronics, all those things are interconnected with each other. So the combination of all those things will meet the energy demand in the upcoming years. So that's all from my side, and session is open for questions. Thank you. Kishore sir. Tripti ma'am, I have finished in time, I think so.
Yes, sir. Before we move on to the question and answer session, I request all the participants to kindly switch on their video for for a screenshot. Dear participants, kindly switch on your video for yes. Thank you, all the participants. Now I request the participants to raise their questions. You can unmute yourself and pose your questions to the speaker.
I think Sunil sir has raised his hand. I think so. Sir, you can give your questions, sir.
Any question from the participants?
Hello, sir. Am I
Yes,
audible?
sir. Yeah.
Yes, sir, you're audible.
Sir, regarding solar specification or requirement, as you said in your slides. So, what is the exact role of reactive power control in solar grid? And frequency control is the one of the issue. And similarly, you are told about the fault right through. So, how we can do the solution for that? Is any artificial intelligence technology we are using for that?
Sir, as I told you, when you go for the grid side, as I told you, few of the things. Sir, grid side, when you're connecting the when you're connecting your output of either from your solar or wind to the grid, there are certain, because there is something called a synchronization, which we are usually talking of frequency matching, because whatever the power we are getting from solar panel or wind, the frequency should be matched with respect to the grid frequency. So there, in that case, to optimize your or to generate the corresponding switching pulses for your inverter circuit, as you can go in optimization techniques, or you can go for an AI technique to produce the required output and to match your frequency with respect to the grid frequency. So you can use any artificial technique. That's why now most of the researchers, what they're doing is they're start using these optimization techniques to improve the efficiency or to make your switching what you call as power transfer circuit to operate at a very higher speed, such that the required frequency can be matched at a faster rate with the grid, so that there will be the problem of fault right through, or the problem of mismatching of the frequency or the voltage frequency can be reduced. Yes, AI technique can also be used to overcome the issues of mismatching frequency or fault right through. Yes, sir. You can use it.
Yes, sir. Yes, sir. Thank you, sir.
Again, you want to pick out the level of voltages at which you are connected with grid, sir. That is one thing you want to also take care before connecting to the grid, sir.
So, sir, park transformation is one of the thing is happen in that case. So, have you elaborate something about the park transformation?
You are talking about power transfer or park?
arc transformation is the one of the DQ axis transformation is there
Yeah.
regarding the solar.
Park transformation is nothing but the what you call is you are classifying the entire thing into two quadrant axis D and Q, quadrant axis and D and direct axis and the quadrant axis based upon the level of what you call as the power level at which the base of the power level and the angle at which the matching or the frequency matching or the voltage level matching can be embedded such that the level of or the angle between D and Q can be matched in such a way the required output will be there with overcoming the drawbacks of this voltage level and the power levels.
Thank you, sir.
Yeah.
Hello, sir. Hello.
Yes, sir.
Yeah, I am Ilango, sir. Hello.
Yes, sir. Yes, sir. Listening.
Now only I'm starting my research regarding this energy management harmonic compensation of DC microgrid using IoT-based decentralized control architecture.
Okay.
So how can I split my module? Which area I can able to concentrate, and what are the most advanced controllers recently available for this? How can I split this module, sir? Harmonic compensation, IoT based.
Yeah, when you talk about the harmonics, sir, harmonics, many of them are thinking the current. There is something in harmonics. There are two terms. One is THD, another one is TDD. So most of the you are using THD, we are using, and many of them forget to go for TDD. So when you talk about this harmonics in the case of micro, whatever the grid you are trying to say, sir, concentrate more on the what you call as converter and the controller side, sir.
Okay, sir.
Because converter, when you talk about, there are n number of controllers. As I said, as I shown you, a lot of controllers depends upon the voltage level, where you can use those type of controllers, and the control technique, as the topic mentioned, lot of AI control techniques are available. Okay, so you can determine the different voltage levels, and you can choose. You can go with the start from the basic of whatever the research areas that we are searching. Start with the basic research paper. Try to go for hybrid controllers, because individual controller already many of them have started using.
Okay, sir.
And IoT is one of the technique which everybody are working on this particular thing. Before going for IoT is at the later stage, sir. Before that, the same converter and the controller has to be keenly understand, utilized, so that the final thing can be go for the IoT device, sir. You concentrate more on the converter and the controller side only, sir. Later, you can go for IoT, sir.
Okay, sir. Thank you, sir. Thank you, sir. Thank you so much, sir.
Thank you, participants, for the questions.
Okay, thank you, madam.
I request Kishore sir to.
Yeah, thank you, Tripti madam. Thank you, sir. Pushpa sir, thank you for your elaborated and very detailed. Actually, you have shown the value of power electronics.
हे आता फिर लागते 5 किलो वजन वाढलं महाराज 80 झाले आज वजन केलं 80 किलो झालं.
Participants, kindly mute yourself.
फिरा पाहिजे आता.
Tripti madam, please sir mute.
कसं होतं काका? नमस्कार हो सर.
Madam, please make Sunil sir.
कसं काका तुमचं कृपा काय?
Yeah, thank you, madam. Yes, Pushpa sir, you have shown the real value of electrical and electronics engineering, that too the part of power electronics in it. Thank you so much, sir. And dear participants, this is the value of power electronics. So you can get the knowledge of power electronics, and you can make use of the power electronics in your further research also. So in this context, we are welcoming all of your participants to join hands with Jain University also. Okay, I am disclosing this one means maybe 2 days is left out for our PhD program. So if you any one of you can join as scholars, you can join and you can apply through website. Okay. For more information, you can contact me directly. And as a coordinator, I am really thankful to all the participants with very little glitches. We have finished today's program, and my sincere request would be all the participants should be muted. Then the speaker will get very good interest, and if everything is calm, then he can speak nicely. And whenever there is a chance given to you for asking the questions, you can ask the questions. And remaining times, whenever you get any doubt, immediately you can put it in the chat window, so that immediately maybe somebody can read them, even resource person can read them, and he can keep on giving the answers. Okay, so this is the way we need to maintain. And thank you so much for your kind cooperation, each and everyone. And thank you so much. And I say good night from my side, and over to Trupti madam. Thank you, madam. Thank you so much. Trupti madam.
Thank you, sir, for giving the insights on the second session. Tomorrow, I just want to give information about tomorrow's session. Tomorrow there will be 2 sessions. Session 3, which is going to begin at 6 p.m. The topic is grid integrated solar energy conversion system with AI. And the speaker for this session is Dr. Animesh Kumar Sahu, who is an associate professor from IIT Dharwad. And the 4th session will begin at 7:30 p.m. on the topic smart utilization of renewable energy resources with AI. And speaker of this session is Dr. Kumaravel, associate professor, NIT Calicut. So I request all the participants to join back for the tomorrow's session at 5:50 p.m. And thank you all the participants for being present for both the sessions, session 1 and session 2. And once again, I request all the participants to kindly fill the feedback form, which is shared in both chat box as well as the WhatsApp group. Kindly fill both the feedback forms. And thank you all for attending the session. See you tomorrow.
Sorry for interrupting in between.
Yes, sir.
Ma'am, if you share materials, that is very much useful for us.
Yes, sir, sure, sir.
Okay, okay, madam.
We'll collect all the materials and PPT from the speakers, and we'll be sharing it, sir. Surely we'll do it, sir.
Okay, madam. Thank you.
Thank you.
Excuse me, madam. Dear participants, we are collecting the PPTs. Okay, so for today's session, PPTs will be shared by tomorrow morning. Okay.
Thank you, sir. Thank you. Thank you.
This will be the culture, and the last day before the exam only we will share it. Okay. And my sincere request would be to get the certificate. Attendance is very much mandatory. It is 80%, and you need to get 70% of marks. For getting 70% of marks, we strictly follow only PPTs. Okay. If you read or if you scroll PPTs one time, that's fine for your preparation. Okay, so no need to worry much, but try to utilize the PPTs properly. That's fine for us. Okay, we will give 50 questions. Maybe if you get more than 35, then you will get the certificate. Okay, and if you have any more doubts also, you can directly message us so that we can give the reply. Understood? Thank you. Thank you so much. Thank you, madam.
Thank you.
Yeah, Trupti madam, you have to end the meeting. Okay. Not the not the just leaving the meeting, just you have to end the meeting.
Sure, sir. Okay, sir. Thank you all, and good night, and have a